Hello there, and welcome to Physics with William, where curiosity settles in for the evening and science is allowed to take its time. Tonight we're turning our attention to something so small that no eye has ever seen it directly, and yet so important that nearly every atom around you depends on it. This subject is the neutron, that quiet resident of the atomic nucleus that tends to receive less public attention than its more sociable partner, the proton, and far less dramatic reputation than the electron, which spends its time darting about like it has forgotten where it left its keys. The neutron does not carry electric charge, it does not advertise itself with sparks or static, and it rarely appears in the everyday metaphors people use when they talk about the building blocks of matter. But it sits at the centre of ordinary substance with remarkable patience, helping hold together the cores of atoms, shaping the stability of elements, and participating in some of the most important events in the history of the universe. And if we ask a question that sounds simple enough to fit in a single sentence, what happens inside a neutron? We find ourselves standing at the entrance to one of the strangest stories in modern physics. Before we ease into that, I would love to know where you're listening from tonight and what sort of hour has found you. Is it late where you are, with the room already dim and the day mostly behind you? Is it early, with the light still hanging about and the mind not quite ready to slow down? There is something fitting about asking that at the start of a discussion like this, because the neutron belongs to a world that is always with us and almost never noticed. It is in the table, the walls, the air, the glass, the fabric, the metal frame of a lamp, the body you're resting in right now. It is part of the ordinary structure of matter, and yet the closer physics has looked, the less ordinary it has seemed. If you find this kind of quiet exploration soothing, or interesting, or simply a pleasant way to let the day loosen its grip a little, I would be very grateful if you gave the video a like and maybe subscribed. It helps this small corner of calm science find the people who enjoy wandering through these questions at a slower pace. Now then, let us begin as gently as we can, because the neutron is not merely a tiny ball sitting inside the atom like a pea in a pod. That picture is understandable, useful for a first introduction, and also badly incomplete. If you learned about atoms in school, chances are you were given a model that looked tidy and manageable. At the centre was the nucleus, made of protons and neutrons. Around it moved electrons. The protons were positively charged, the electrons negatively charged, and the neutrons neutral, which made them sound almost like administrative staff in the office of matter. Important, certainly, but not where the action was. The name itself encourages that impression. Neutron. Neutral one. The particle defined at first glance by what it lacks. No electric charge, no bright external signal, no immediate personality. Yet that very absence is part of what makes it so interesting, because neutrality at the surface does not mean emptiness underneath. A neutron is not blank, it is not inert. It is not some featureless bead parked inside the nucleus for structural support. Inside the neutron there is movement, tension, exchange, confinement, and an astonishing amount of physical activity packed into a region so small that even the word small begins to feel lazy. This is one of those places where common sense serves well, right up until it does not. In daily life, if something has no net charge, we tend to imagine it as balanced in a static way. Nothing to see here. The books on one side of the shelf match the books on the other. The scale reads 0. The matter is settled. But in particle physics, 0 on the outside can hide a very busy interior. A neutron has no overall electric charge. That part is true, but the ingredients inside it are themselves charged. Their arrangement, motion, and interaction produce an object that ends up neutral as a whole, much like a well-run kitchen can look calm from the dining room, while behind the door people are moving quickly, passing hot pans, coordinating timing and trying not to drop anything expensive. If that makes the neutron sound less like a marble and more like a confined storm, that is closer to the mark. To appreciate why physicists became so interested in what happens inside a neutron, It helps to remember that the neutron itself was once a discovery that solved a serious problem. Early atomic models ran into a puzzle. Atoms had a central nucleus with positive charge, and the number of protons explained the identity of each element. But the mass of nuclei did not line up neatly if protons were the only heavy particles present. Something else seemed to be there, adding weight without adding charge. For a while this was mysterious. Then, in the early 20th century, the neutron was identified, and suddenly the nucleus made much more sense. Here was the missing mass, the neutral partner that helped explain why nuclei could be heavy without being impossibly overcharged. It was a major step forward, and for some time the neutron itself was treated as a basic particle, one of the fundamental ingredients of matter. That view did not survive. Physics has a habit of accepting a clean answer for a while, then returning later with a more complicated question. As experiments improved, especially in the middle of the 20th century, scientists learned that protons and neutrons were not fundamental after all. They belonged to a family of particles that showed internal structure, and eventually the quark model emerged. According to that picture, the neutron is made of 3 quarks as its core ingredients, held together by gluons, the carriers of the strong interaction. That sentence is often where popular explanations pause, as though the mystery has been respectfully folded and placed back in a drawer. The neutron contains 3 quarks. Very good. Case closed. But that sentence is only the beginning. It is like being told a city contains roads, buildings, and people. True, certainly, but not yet enough to understand traffic, power, noise, commerce, construction, weather, or why one street is impossible at precisely the wrong hour. Saying that a neutron contains quarks and gluons is not the end of the story. It is the first map sketch drawn before the hard work starts. What makes the neutron especially fascinating is that its insides do not behave like little solid pieces packed together in the ordinary mechanical sense. The world inside a neutron is governed by quantum physics and by the strong interaction, the force that binds quarks together with such intensity that they are never found isolated in normal conditions. You do not take a neutron apart the way you might open a watch. There is no tiny hinge, no shell to lift, no orderly cross-section waiting like a textbook diagram come to life. The deeper you probe, the more energetic the process becomes, and instead of peacefully extracting the contents one by one, you tend to create new particles. It is a bit like trying to inspect the inside of a tightly wound spring by hitting it with a hammer, and discovering that the hammer blow changes the whole situation. Physicists have learned a great deal about neutrons, but they have had to do it indirectly, carefully, and with no shortage of mathematical persistence. That alone should make the neutron feel less like an old familiar item from school science, and more like an active frontier. It is one of the reasons the question guiding us tonight is worth asking in the first place. What happens inside a neutron is not merely a question about composition. It is a question about motion, about energy, about how matter gets its properties, about why some particles remain bound while others decay, and about how something that appears simple at first can turn out to be richly structured when examined at the right scale. This is one of the recurring lessons of physics. The closer we look, the less the world resembles the neat wooden blocks of our intuition. Instead, we find layers of behaviour, each one with its own rules, each one answering an old puzzle while introducing a new one. There is another reason the neutron deserves a slower introduction. Although it is central to ordinary matter, a free neutron is not stable forever. Inside many atomic nuclei, neutrons can remain bound and persistent. Left on its own, however, a neutron eventually decays. That fact alone tells us something important. The neutron is not a frozen unit. It has internal rules and possible transformations. It lives within a web of interactions that allow it, under the right conditions, to change into something else. So even before we explore the details of quarks and gluons, we already know the neutron cannot be just a passive lump. It has an inner life in the physicist's sense of the phrase. Processes are available to it. Energy is arranged in particular ways. Stability depends on context, and context, as it turns out, matters enormously in the small world. At this point, it is tempting to picture ourselves shrinking down, passing through the outer regions of an atom, and approaching a nucleus as though we were moving towards some tiny compact object in a clear empty space. That sort of guided miniature journey can be useful, and perhaps also slightly misleading. At atomic scales, familiar ideas like surface, hardness, and location begin to lose their comfortable meanings. A nucleus is not a little billiard ball. A neutron inside it is not a pea rolling around in a box. These are quantum objects described by probabilities, interactions, and fields. Still, the imagination needs something to work with, so let us use our images carefully. Think less of a neutron as a fixed object with a quiet centre, and more as a stable pattern maintained by intense internal rules. It is a persistent arrangement, a durable identity, a thing, yes, but a thing made of activity rather than stillness. That point may sound subtle, but it matters. In everyday language, we treat objects as things that possess properties. A chair has weight, colour, shape, and position. A stone has size and density. We think of the object first and the behaviour second. In particle physics, that order can reverse. The behaviour and the allowed interactions are often what define the object. A neutron is what it is because of how its constituents abound, how they move, how the strong interaction operates among them, and how the resulting whole behaves in experiments. Remove those interactions and the neutron does not simply become a smaller neutron. It stops being a neutron at all. This is why asking what happens inside one is not like asking what is stored inside a box. It is closer to asking what ongoing processes make the box meaningful in the first place. Except, of course, that no actual box is involved, which is probably for the best because quantum mechanics has enough of those already. There is also a pleasing historical irony here. For centuries, science often advanced by dividing matter into smaller and smaller pieces in thought. Molecules into atoms, atoms into nuclei and electrons, nuclei into protons and neutrons into quarks. That sequence can encourage the impression that understanding means finding the smallest hard pellets and naming them correctly. But when we arrive at the neutron and look within, the story shifts. Yes, there are constituents, but there is also a surrounding sea of activity, transient pairs, exchanged gluons, and collective dynamics that matter just as much as the list of ingredients. In other words, the neutron is not simply a sum of three little items. It is a highly organised quantum system, and much of its character emerges from that organisation. This is one reason modern particle physics can be so counterintuitive. It does not just ask what something is made of, it asks how the patterns of interaction produce the thing we recognise. All of this might raise a fair question. If the neutron is so complicated, why does it appear so ordinary in the larger world? Why do tables not tremble with quantum uncertainty? And why are not nuclear particles introduced at dinner parties with the respect reserved for unstable geniuses? The answer, as usual, is scale. The internal drama of the neutron is real, but it is confined to a realm so small and so effectively self-contained that the larger world averages over it. Matter becomes stable enough for chemistry, solid enough for engineering, and calm enough for us to put down a cup without consulting a particle detector. That is one of the quiet triumphs of nature. Beneath the ordinary reliability of the visible world lies an astonishing amount of microscopic complexity, and somehow the whole arrangement holds together well enough for everyday life to proceed, with only occasional reminders from radioactive decay, particle accelerators, and the stars. And the stars do matter here, because neutrons are not merely laboratory curiosities. They play a major role in astrophysics, nuclear reactions, and the history of the elements. In violent cosmic environments, neutrons help shape what matter becomes. In the remains of massive stars, matter can be compressed so far that neutrons dominate on a scale almost beyond imagination. A neutron in your body and a neutron in a distant stellar remnant obey the same basic laws, even if the conditions around them differ wildly. That continuity is one of the great strengths of physics. The same small particle can help explain both the structure of an atom and the fate of a collapsed star. So when we ask what happens inside a neutron, we are not asking an isolated technical question. We are touching a subject that reaches from the nucleus of the simplest matter all the way to some of the most extreme objects in the universe. For now, though, we do not need to rush outward to the stars or downward too abruptly into quark-level detail. It is enough at this stage to settle on the central fact that the neutron is active inside, not blank. Neutral, yes, simple from a distance perhaps, fundamental in importance, certainly, but internally it is made of charged quarks bound by gluons, shaped by the strong interaction, surrounded by quantum activity, and defined by motion and exchange as much as by composition. That is the doorway we will continue through. Once it opens, several questions follow naturally. If quarks are inside the neutron, how exactly are they arranged? What keeps them bound so tightly that they never appear alone? Why does the neutron have the mass it does? What does it mean for it to have spin if nothing in that world behaves like a tiny spinning top? Why can a neutron remain stable inside some nuclei and decay when free? And how do physicists know any of this if they cannot open one up and have a tidy look around? Those are the questions waiting ahead, and they reward patience. The neutron is one of those subjects where each answer improves the picture only by making it stranger in a more precise way. That, oddly enough, is reassuring. It means we are not dealing with mystery because nobody has looked carefully. We are dealing with mystery because people have looked very carefully indeed, and the universe has turned out to be under no obligation to make itself resemble our first sketches. If anything, the neutron teaches modesty. It reminds us that even an apparently quiet particle at the centre of matter can contain a whole hidden economy of interactions, and that some of the most important structures in nature do their work without much advertisement. So as we move further into this topic, keep that original question nearby. What happens inside a neutron? Not what is it called in a school diagram, and not what quick label can we attach to it and then move on, but what is actually going on in there? What motions, what exchanges, what constraints, what restless processes give rise to this neutral resident of the nucleus? Once that question is taken seriously, the neutron stops being a supporting character and becomes one of the most revealing places to study matter at its deepest accessible level. And the next step is to look more directly at the particle itself, not yet at every internal detail, but at what sort of object the neutron is when viewed in the broader company of atoms, nuclei, and the family of particles that make up the visible world. If the neutron were the sort of particle that cared about public image, it might reasonably file a complaint. The electron gets all the quick recognition because it is light, fast, and easy to blame for electricity, chemistry, and the occasional static shock on a winter evening. The proton sounds important from the start, partly because it carries positive charge and partly because it sits in the nucleus with an air of official business. The neutron, by contrast, arrives in most early science lessons as the quiet one. Neutral. Heavy enough to matter, certainly, but not flashy, not dramatic, not the one children are encouraged to picture zipping around or pulling clever tricks. It tends to be introduced as though its main contribution is showing up, keeping the nucleus company, and refraining from causing electrical trouble. That first impression is not exactly wrong, but it is incomplete in a way that hides just how central the neutron really is. The neutron is quiet only in the sense that it carries no net electric charge. It is not quiet in importance, it is not quiet in consequence, and it is certainly not quiet on the inside, as we will soon see. But before we go inward, it helps to stay for a while with the neutron in its larger setting, because its role at the heart of matter is easy to underestimate if all we remember is the schoolroom summary that atoms have protons and neutrons in the middle and electrons around the outside. True enough, useful enough. Yet that tidy picture conceals a remarkable fact. If neutrons did not exist, or behaved a little differently, much of the ordinary material world would be unrecognizable. To see why, begin with the nucleus itself. The atomic nucleus is a crowded place, especially when compared with the rest of the atom. Most of an atom is empty in the everyday sense that its mass is concentrated in a tiny central region, while the electron cloud extends much farther out. That central nucleus contains protons and neutrons packed together at distances so small that the forces between them are enormous by ordinary standards. The protons all carry the same positive charge, which means they electrically repel one another. Left to that effect alone, a nucleus with more than a single proton would be a very poor long-term arrangement. It would come apart almost immediately. Yet nuclei do exist, and many of them are stable for vast stretches of time. Something must be overcoming that electrical repulsion at very short range. Part of that story involves the strong interaction acting between the particles in the nucleus, but the neutron is essential to how the balance works in practice. A neutron does something very useful. It contributes to the binding of the nucleus without adding more electric repulsion. A proton brings mass and a positive charge. A neutron brings mass and no net charge. That combination turns out to be exactly what atomic nuclei need if they are to grow beyond the very simplest cases. If you tried to build large nuclei using protons alone, the repulsion would become overwhelming. Add neutrons, however, and you can increase the attractive nuclear binding without making the electrical crowding worse. The neutron is not a passive filler in this arrangement. It is an active participant in the force balance that lets atomic nuclei exist at all in a wide range of sizes. In a sense, the neutron is what allows matter to become varied rather than remaining stuck at the bare minimum. This matters more than it may sound. When physicists and chemists talk about elements, they usually refer to the number of protons in the nucleus as the defining feature. That is true. Change the proton number and you change the element. Carbon is carbon because it has 6 protons. Oxygen is oxygen because it has 8. Gold is gold because it has 79. But the number of neutrons can vary even while the proton number stays fixed, and those variations create isotopes. Isotopes are versions of the same element with different numbers of neutrons. Chemically, they are very similar because chemistry is mostly about electrons and charge balance. But physically and nuclear-wise, they can behave quite differently. Some isotopes are stable, some are radioactive, some are common in nature, some are rare or short-lived. The neutron is therefore part of what gives matter internal variety even when the element name remains the same. That idea is worth lingering over because it gives the neutron a surprisingly broad reach. The water you drink, the carbon in your cells, the calcium in your bones, the iron in your blood, all of these depend not only on protons but on particular neutron counts that make certain nuclei stable enough to persist. The periodic table often appears as a chart of proton identity, and rightly so. But the actual landscape of matter is also shaped by how neutrons are distributed. In that sense, the neutron helps determine not merely whether a nucleus can exist, but which versions of familiar elements are common, stable, and useful in the world around us. It is one of the reasons the neutron belongs in the center of the conversation about ordinary matter, rather than sitting politely off to one side. There is also a historical reason the neutron felt so important once it was discovered. Early atomic theory had a problem. The positive charge of the nucleus could be accounted for by protons, but the masses of many nuclei were too large to be explained by protons alone if charge balance was to make sense. Something heavy and electrically neutral seemed to be missing. When the neutron was identified in the early 20th century, it filled that gap beautifully. Suddenly physicists had a way to explain nuclear mass without cluttering the nucleus with impossible extra charge. That was a major conceptual advance. It made the nucleus more intelligible. It also helped explain why isotopes existed. A carbon nucleus with 6 protons and 6 neutrons is one thing. A carbon nucleus with 6 protons and 8 neutrons is another. Same element, different mass, different nuclear behavior. Once the neutron entered the picture, those patterns became much easier to understand. Even so, there is something slightly deceptive about the way the neutron solved that puzzle so neatly. It made the nucleus more comprehensible, but it also introduced a new character whose own nature would turn out to be more complicated than anyone first guessed. For a while, the neutron was treated as a fundamental particle, one of the basic building blocks. That was a reasonable view at the time. It had mass, it lived in the nucleus, it carried no net charge, it looked elementary enough. Later work changed that picture, but for the moment it is useful to stay with the older perspective just long enough to appreciate how the neutron behaves as a citizen of the atomic world. One of its most striking features is that it makes itself known through nuclear effects rather than electric ones. The proton announces itself through charge, the electron does the same. Their presence can be inferred from electric fields, chemical behavior, and electromagnetic interactions of all kinds. The neutron slips past many of those obvious routes. Because it is electrically neutral, it does not push or pull on charges in the same direct way. That neutrality makes it harder to corral using electric fields and easier, in some circumstances, to send into nuclei. It also makes neutrons extraordinarily useful as probes in experiments. A charged particle approaching a nucleus feels electric forces immediately. A neutron can come closer before those particular complications dominate. This has made neutron beams valuable in studying the structure of materials, the arrangement of atoms in solids, the motion of magnetic moments, and a range of other phenomena. Once again, the supposedly quiet particle turns out to be quietly useful in ways that charged particles are not. There is a subtle point hidden there. Neutral does not mean non-interacting, it only means no net electric charge. Neutrons still participate in the strong interaction. They still have magnetic properties because of their internal structure. They still respond to gravity, although that is negligible at these scales. They can still collide, scatter, bind, decay, and influence the fate of nuclei. So when we call the neutron quiet, we should really mean that it is not electrically loud. That is a much narrower statement. In every other relevant sense, the neutron is deeply involved in the architecture of matter. Consider what happens in the simplest nuclei. Hydrogen, in its most common form, has a nucleus made of a single proton and no neutron at all. It is the minimal case, the bare-bones version of atomic structure. Add one neutron and you get a heavier form of hydrogen. Add another, and you get a still heavier one, though no longer stable. Already the neutron count is changing the character of a familiar element. Move to helium, carbon, oxygen, or iron, and the pattern becomes richer. The ratio of neutrons to protons helps determine whether a nucleus sits comfortably in a stable arrangement, or whether it is prone to decay into something else. For light nuclei, equal or nearly equal numbers of protons and neutrons often work well. As nuclei grow larger, more neutrons are generally needed than protons to maintain stability. That trend reflects the increasing challenge of managing proton repulsion in a larger nucleus. Neutrons help by contributing attractive nuclear effects without worsening the electrical congestion. This balancing act is one of the great organizing principles of nuclear physics. It is not perfect, and it is not infinitely flexible. Add too few neutrons and a nucleus may become unstable. Add too many and different kinds of instability appear. Nature allows a broad range of nuclei, but not every imaginable combination. There is a kind of nuclear geography here, with islands of stability, coastlines of decay, and regions where matter exists only briefly before transforming. The neutron is one of the main variables in that geography. A nucleus is not just a count of charge. It is a negotiation between attraction, repulsion, mass, quantum rules, and the specific numbers of protons and neutrons involved. That negotiation extends into the life stories of stars. Inside stars, nuclear reactions build heavier elements from lighter ones. Those reactions depend on the detailed behavior of nuclei, and neutron-related processes play a major role in how the periodic table is assembled over cosmic time. In more violent environments such as exploding stars or collisions between extremely dense stellar remnants, rapid neutron capture can drive the creation of heavy elements that ordinary stellar burning cannot easily make. Gold, platinum, and other heavy nuclei owe part of their existence to conditions in which neutrons become available in large numbers, and nuclei can absorb them rapidly. So when you hold a metal object, wear a ring, or think about the elemental composition of the Earth, you're not far from the neutron story. It helped shape which nuclei were forged and which survived. The neutron is also unusual in another way that often surprises people once they first hear it. A neutron bound inside a stable nucleus can last indefinitely as part of that nucleus. A free neutron, drifting alone, does not. It eventually decays into other particles. That contrast is telling. It means the neutron is not simply a little hard pellet, with an unchanging identity regardless of surroundings. Context matters. In a nucleus, the balance of energies and interactions can make the neutron effectively stable. Outside a nucleus, a different set of possibilities opens, and decay becomes allowed. This makes the neutron a useful reminder that particle behavior often depends on the larger system in which the particle sits. The same object can be persistent in one environment and temporary in another. That fact has practical consequences in laboratories and reactors. Free neutrons can be produced and studied, but their fleeting nature means experiments must account for decay. Their neutrality also makes them both useful and inconvenient. Useful because they can penetrate matter in ways charged particles cannot. Inconvenient because steering them is harder. They do not obediently curve in electric fields like electrons or protons. They require different handling, different detection methods, and a certain amount of experimental ingenuity. This has given neutron physics a somewhat distinctive character. It is not merely a copy of charged particle physics with one feature turned off. It is its own craft. There is something else worth noticing here. The neutron sits at an interesting middle scale in the hierarchy of matter. It is smaller than atoms and nuclei as a whole, but larger in a meaningful structural sense than the truly elementary particles we currently know, such as electrons. It belongs to the family of hadrons, particles made of quarks and governed internally by the strong interaction. That gives it a double identity in the history of science. On the one hand, it is one of the classic nuclear particles, familiar from the basic anatomy of the atom. On the other hand, it is a composite object with an internal world that modern particle physics has had to uncover piece by piece. This double role is part of why the neutron is such a satisfying subject. It links the ordinary matter of daily life to the deep theory of quarks and gluons. Yet before we turn fully to those internal constituents, it is worth asking what people mean when they call the neutron one of the building blocks of visible matter. The phrase is accurate but slightly delicate. Visible matter, the ordinary matter that makes up stars, planets, air, rocks, living tissue and furniture of varying quality, is made mostly from atoms. Atoms contain nuclei, and nuclei often contain neutrons. In that practical sense, neutrons are absolutely among the building blocks, but they are not fundamental in the deepest current theory. They are built from smaller constituents. This is not a contradiction. It simply reflects that building blocks can exist at different levels of description. Bricks are building blocks of a house, even if the bricks themselves are made of minerals. Neutrons are building blocks of atomic nuclei, even though they themselves have internal structure. Once that is appreciated, the neutron becomes even more interesting, not less. If it were truly elementary, there would be less to say about what happens inside it. Important things would still happen around it, certainly, but the internal question would become much thinner. The discovery that the neutron is composite transformed it from a stabilizing unit of nuclei into a dynamic system worthy of study in its own right. Its mass, its magnetic behavior, its spin, its decay, and even its neutral charge all now had to be understood as consequences of deeper ingredients and the rules binding them together. This shift in perspective also helps explain why modern descriptions of matter often feel less like lists of parts and more like accounts of relationships. When matter was imagined as stacks of tiny, hard, indivisible pieces, understanding could seem like a matter of naming the pieces correctly and arranging them neatly. But a neutron is not an indivisible pebble. It is a bound state. It exists because certain constituents interact in a very specific way. Much of what the neutron is comes not from a simple inventory, but from the dynamics of confinement, exchange, and motion within it. Even its mass is not just the sum of a few bare ingredients. A large share of what we call the neutron comes from the energy of the strong interaction itself. So the quiet particle at the heart of matter is also a lesson in how deeply modern physics has moved beyond the old image of matter as a pile of little inert chunks. There is an understandable temptation, when discussing things this small, to imagine we are simply discovering ever tinier objects in a fixed chain downward. But the neutron resists that picture. It reminds us that structure is not always about smaller and smaller hard pieces. Sometimes it is about patterns that only exist because forces and quantum rules hold them together. A neutron is real, stable enough in many settings, measurable and indispensable, yet it is also inseparable from the activity inside it. Take away that activity and the neutron does not remain behind as a neat reduced core. It vanishes as the particular thing it was. This is where the story begins to shift from the neutron as a nuclear resident to the neutron as an internal world. Up to now, we have been looking at what the neutron does in matter, why it matters for nuclei, why neutrality is useful, why isotopes exist, why stellar chemistry owes it a debt, and why a particle that sounds modest turns out to be central. All of that gives us the right respect for the neutron before we ask the more intimate question. If it is so important, if it is so active in shaping matter, and if it is not fundamental after all, then what exactly is going on inside it? What makes a neutron instead of some other hadron? Why does it have no net charge despite being made of charged constituents? Why is it as heavy as it is? What holds it together so fiercely that its parts do not wander off on their own? Those questions take us away from the atom as a whole, and toward the far denser level beneath the nucleus, where the neutron stops looking like a compact neutral unit and starts revealing the three quarks at its core, along with the force carriers and restless quantum activity that make its apparently calm exterior possible. Once we stop looking at the neutron as a useful resident of the atomic nucleus and start treating it as an object with an interior life of its own, the first surprise is that it does not open up into anything like the neat mechanical pictures our everyday instincts would prefer. There is no tiny shell to lift, no little compartment inside, no miniature beads stacked quietly in a row, waiting to be counted like screws in a drawer. What modern physics tells us instead is that the neutron has, at its core, three quarks. That is the standard opening statement, and it is a good one as far as it goes. But it can also be misleading if it sounds too tidy. Three quarks are indeed central to the neutron's identity. Yet the phrase can tempt the mind into imagining three small hard objects sitting obediently close together in a confined space, perhaps like three people in an elevator, trying very hard not to make eye contact. The truth is both more precise and more strange. The neutron belongs to a family of particles called baryons, and baryons are built from three valence quarks. Those valence quarks are the essential quark ingredients that give the particle its overall quantum identity. In the case of the neutron, the combination is one up quark and two down quarks. That combination matters because quarks carry electric charge, and the charges of these particular quarks add up to 0 overall. The up quark carries a positive fraction of the proton's charge, while each down quark carries a negative fraction. One positive fraction and two negative fractions balance to neutrality. So the neutron's lack of electric charge is not a sign that nothing charged exists inside it. Quite the opposite. It is the result of a very specific combination of charged constituents that cancel at the level of the whole. This already tells us something important. Neutral on the outside does not mean simple on the inside. A neutron may not announce itself electrically in the way a proton does, but its internal ingredients are charged and active. The same is true in reverse for the proton. The proton is made of 2 up quarks and 1 down quark, which gives it a positive net charge, so proton and neutron are closely related. They are almost like siblings built from the same kinds of ingredients, differing only in the balance. That likeness is one reason they behave similarly in many nuclear situations, but the difference matters enough to shape the structure of atoms and the chemistry of the world. Still, even after naming the quarks, we have not yet answered the deeper part of the question. What are those 3 quarks actually doing in there? Are they orbiting? Are they stationary? Are they arranged in a triangle? Do they take turns being in the middle? Do they politely stay in their assigned positions? The answer, unsurprisingly, is that they do none of those things in any ordinary classical sense. Quarks are quantum objects. They are described by wave-like behaviour, probabilities, and allowed states rather than little defined tracks. If you try to picture them as tiny marbles moving along miniature paths inside the neutron, the image breaks down very quickly. It is better to think of the neutron as a tightly bound quantum system in which the quarks are confined to a very small region by an extremely strong interaction. They are not little passengers sitting inside a container. They are part of a whole pattern that only exists because of the forces and rules tying them together. The word confined matters a great deal here. Quarks are not found alone in ordinary conditions. No one has ever plucked a single quark out of a neutron and placed it gently on a tray for inspection, and this is not because experimental physicists lack curiosity or suitably dramatic machinery. It is because the strong interaction behaves in a way unlike the familiar forces of daily life. In many ordinary systems, pulling things apart weakens their connection. Stretch a spring too far and it may eventually separate or snap. The strong interaction does not give you that luxury. As quarks are pulled apart, the energy in the connection between them increases so much that instead of isolating one quark, the system tends to create new particles, so the quarks remain confined. They live in a very small room, but not one with walls made of solid material. The room is built from the rules of quantum chromodynamics, the theory that describes the strong interaction. That name may sound imposing, but its basic purpose is clear enough. It is the framework physicists use to explain how quarks interact by exchanging gluons. Gluons are the carriers of the strong interaction, rather as photons carry the electromagnetic interaction. But while that comparison is helpful at first, it should not be pushed too far because gluons are much more troublesome company. Photons do not carry electric charge, so they do not directly tug on one another. Gluons do carry the relevant type of charge for the strong interaction, which means they interact with each other as well as with quarks. The result is a theory with a great deal of internal complexity. The neutron is therefore not just 3 quarks sitting around a table, it is 3 valence quarks embedded in a ceaseless exchange of gluons, with all the tension and motion that implies. Before we get to the gluons in full detail, it is worth staying a little longer with the quarks themselves. The idea that the neutron contains 1 up quark and 2 down quarks is not merely a label. It explains several of the neutron's most important properties. We have already mentioned charge. It also helps explain why the neutron and proton are similar in mass but not identical. Up and down quarks are very light in terms of their bare masses, and they're close to one another, though not exactly equal. Yet if you add up the bare masses of the valence quarks, you get only a small fraction of the neutron's total mass. That fact is one of the first signs that the neutron is not simply the sum of 3 tiny ingredients. Most of its mass comes from the energy of the system as a whole, from motion and strong interaction effects. So when we say the neutron contains 3 quarks, we are identifying the main quark pattern, not claiming that 3 little masses added together explain the whole object. There is another subtlety here that often surprises people. The valence quarks are essential, but they are not the only quark activity inside the neutron. The neutron also contains a shifting sea of virtual quark and antiquark pairs that appear and vanish as part of the quantum behaviour of the strong interaction. This means the inside of the neutron is not a clean 3-item inventory. The 3 valence quarks define the identity, yes, but they exist amid a restless background of additional activity. For now, though, the core picture still begins with the valence trio, because those are what make a neutron rather than some other hadron. If you are wondering how something can have 3 main quarks and still contain more quarks in a fluctuating sea, that is a healthy question. The answer has to do with the difference between the fixed identity of the particle and the dynamic quantum processes taking place within it. The valence quarks determine the neutron's defining quantum numbers. The C quarks are transient contributions arising from the interaction field. A useful comparison, though not a perfect one, is to imagine a business with 3 official partners whose names are on the door, while a shifting crowd of consultants, messengers, and temporary staff constantly moves through the building. The identity of the business depends on the named partners, but the day-to-day internal activity involves far more people than that. The Neutron is not literally a business, of course, though if it were, the paperwork would be astonishing. The space inside the Neutron is also not empty in the way the word room might suggest. We use that language because it helps the mind accept that 3 quarks are confined to a tiny region, but the Neutron is not a hollow chamber. It is a compact quantum system with a characteristic size of about 1 femtometer, which is an unimaginably small distance by everyday standards. The quarks are not sitting in empty air between fixed boundaries. Their positions and momenta are subject to quantum uncertainty, and the strong interaction fills the region with a dense field of exchange and energy. If an ordinary room were this crowded with interaction, you would not describe it as cozy. You would describe it as an emergency, and yet the Neutron is stable enough in the right setting to persist. That stability is itself remarkable. Think of what is being maintained. Inside an extremely tiny region, 3 valence quarks are confined by a force that does not let them escape, embedded in a swarm of gluonic activity and C-quark effects, all organised in such a way that the whole object has a definite mass, spin, magnetic properties, and charge of 0. This is not a casual arrangement. It is one of the most tightly regulated systems in nature. The rules are strict because they have to be. If quarks were free to wander off, ordinary matter would not look the way it does. One thing that makes this hard to picture is that the quarks inside the Neutron are not assigned fixed classical roles. You cannot point to one and say this one is always on the left, that one is always closer to the centre, and the other one handles the paperwork. Their behaviour is described by a quantum state shared within the bound system. The Neutron has internal structure, but that structure is not like the structure of a toy assembled from rigid pieces. It is more like a standing pattern produced by allowed states and intense interactions. This is why high-energy scattering experiments became so important. Physicists could not simply look inside a neutron with a microscope. Instead, they had to probe it by smashing particles into it and studying how the neutron responded. From such experiments, they learned that the quarks carry portions of the neutron's momentum, that the distribution is not static, and that the internal world is far richer than a simple 3-ball model would suggest. Even the question of how the neutron spin arises turns out to be more complicated than just adding the spins of 3 quarks in the most naive way. Quarks have an intrinsic angular momentum called spin, but the neutron's overall spin reflects not only the spins of the valence quarks, but also their orbital motion and contributions from gluons and C quarks. So the 3 valence quarks are indispensable, but they do not tell the entire story by themselves. Once again, the neutron resists being reduced to a tidy count. It keeps reminding us that identity in particle physics is not just a list of ingredients. It is a full pattern of interaction and motion. That does not mean the 3 quarks are unimportant. Quite the opposite. They are the backbone of the neutron's quark structure. Without 1 up and 2 down quarks in the valence configuration, you do not have a neutron at all. This core arrangement determines the particle family, its charge, and a good deal of its behaviour. It also links the neutron closely to the proton, whose valence structure differs by only 1 quark flavour. That near symmetry between neutron and proton is deeply important in nuclear physics. It helps explain why they are so similar, and why nuclei can treat them as near partners under the strong interaction, even though electrically they differ. The term flavour, by the way, is one of those particle physics words that sounds like it wandered in from a far less serious profession. Quarks come in several flavours, of which up and down are the lightest and most relevant for ordinary matter. There are heavier flavours as well, but they do not play a role in the stable matter around us in the same way. So the neutron is built from the two most familiar quark flavours in the visible universe. That simplicity is deceptive though, because the behaviour produced by those flavours under strong confinement is anything but simple. There is also colour charge, which has nothing to do with visible colour, but is the kind of charge relevant to the strong interaction. Quarks carry colour charge, and gluons mediate interactions among those charges. The neutron as a whole must be colour neutral, just as hadrons generally are. That requirement shapes how the quarks combine. The three quarks in a neutron are arranged so that their colour charges together form a neutral overall state. This is another reason the three-quark structure matters. It is not just about counting flavours, it is also about satisfying the deeper rules of the strong interaction. The neutron is allowed as a stable bound state because the configuration of quarks and colours works out in the right way. At this stage it may sound as though the neutron is somehow overdefined, with charges, flavours, colours, spin states, confinement rules, and quantum uncertainties all piled on top of one another. In a sense, that is exactly right. The neutron is a highly constrained object. It is possible because many rules are being satisfied at once. That is often how stability emerges in physics, not through looseness, but through a tight fit among the allowed conditions. Matter persists because the universe is surprisingly good at producing durable arrangements out of severe underlying rules. The smallness of the neutron also deserves emphasis because it shapes everything about the quark system. The region in which the quarks are confined is so tiny that their quantum motion is significant. You cannot treat them as nearly motionless objects. Their kinetic energy contributes importantly to the neutron's mass and internal state. In the everyday world, if three things are confined to a small space, you may imagine them jostling a bit. Inside the neutron, that jostling is not a side effect. It is part of the essence. The quarks are highly energetic, and the energy bound up in their confinement is enormous compared with what common sense would expect from such small constituent masses. This is one reason the neutron's mass is such an instructive fact. People often assume that an object's mass is mostly the sum of the masses of what it is made from. That works reasonably well for many ordinary systems. A bag of apples weighs about as much as the apples you put into it, unless someone has hidden a bowling ball at the bottom. But the neutron is not like that. The bare quark masses account for only a modest share of the total. Most of the neutron's mass arises from the energy of confined quarks and gluons. It is a vivid demonstration of a deep principle in physics, namely that energy contributes to inertia and mass. The neutron feels solid and substantial at the particle level not because it contains three especially heavy ingredients, but because the binding dynamics are so intense. This should also make us cautious about the phrase inside the neutron. It is useful, but only if we remember that inside does not mean a container with contents the way a lunchbox contains sandwiches. The neutron is the bound state of these quarks and their interaction field. The inside is not a separate place from the neutron itself. It is the neutron's own internal organisation. When we speak of what happens inside it, we mean the structure and dynamics that constitute the particle. The distinction is subtle but important. There is no neutron apart from that activity hiding somewhere behind it like a landlord collecting rent. Still, the image of three quarks in a very small room remains useful if handled gently. It captures the confinement, the crowding, and the fact that these are not distant ingredients. It also hints at the tension. Whatever else is true, the neutron is not a lazy object. Its core constituents are held in an extraordinarily compact and energetic state. They are not there by convenience but by force, and the force involved is the strongest one in the standard model at the scales that matter here. That force is what makes the next step unavoidable. Once you have accepted that the neutron contains three valence quarks, you immediately have to ask what holds them together. Why does this tiny crowded system not simply fly apart? Why do the quarks remain confined? And why does the interaction between them behave so differently from the familiar forces that shape our daily experience? At that point, the spotlight shifts from the quarks themselves to the exchange particles that bind them. Because the room is small, the residents are restless, and the invisible threads between them are doing most of the work. Now we come to the part of the neutron story where the word glue stops sounding like a cute nickname and starts sounding like a serious piece of physics. Once you accept that a neutron is built around 3 valence quarks, the next question arrives almost immediately. What keeps them together? Not in a vague classroom sense, not in the way a diagram labels them and moves on, but in the literal physical sense. Why does a neutron remain a neutron instead of letting its quarks wander off in different directions? The answer is that quarks are bound by gluons, the carrier particles of the strong force, and this force is the strongest of the fundamental interactions at the tiny scales that matter here. CERN describes the gluon as the force carrier of the strong interaction, and both CERN and the United States Department of Energy describe protons and neutrons as objects built from quarks and gluons rather than quarks alone. At first glance, calling them gluons sounds almost too friendly. It suggests a neat, practical service. Things were drifting apart, so nature sent in a small team of subatomic repair workers with adhesive and a positive attitude. But gluons are not tidy little bonds placed between otherwise independent pieces. They are the quanta of the strong interaction itself. They are part of the ceaseless exchange that makes a hadron, including a neutron, into a bound state in the first place. If you take the gluonic activity away, you do not reveal a simpler neutron underneath. You destroy the very process that gives the neutron its identity. In that sense, gluons do not merely hold the quarks together from the outside. Their interaction is part of what the neutron is. That is why modern descriptions of matter sound less like carpentry and more like field theory. The particle is not a thing plus glue. The thing is the pattern of interactions, and the gluons are central to that pattern. To understand why gluons behave so differently from the force carriers we meet in more familiar contexts, it helps to compare them with photons. Photons carry the electromagnetic force. If 2 charged particles interact electrically, photons are the exchange particles in the quantum description. That much is standard. But photons themselves do not carry electric charge, which means they do not directly attract or repel one another in the usual way. Gluons are different. The strong force depends on a type of charge called color charge, and gluons themselves participate in it. Brookhaven National Laboratory explains that, unlike photons, gluons can and do interact with one another, and Jefferson Lab likewise points to gluon self-interaction as a central reason the strong fields are so intense and so important for visible matter. This is one of the reasons the inside of a neutron is such a difficult place to describe with ordinary intuition. If the binding agent also interacts with itself, the whole system becomes much richer and much less obedient to simple mental pictures. The quarks are exchanging gluons, yes, but the gluons are also affecting other gluons. The result is not a static set of links like rods in a model kit. It is a dense, active field structure in which energy is constantly being exchanged. If you try to imagine 3 quarks joined by 3 neat glowing strings and then stop there, you have something more like a first draft than a finished picture. The neutron is closer to a compact storm of quark and gluon activity that remains organized enough to be a particle with definite properties. The word color in all of this is also one of those terms particle physics borrowed from ordinary life and then immediately made less helpful. Quarks and gluons carry color charge, but this has nothing to do with visible color. It is simply the name given to the type of charge relevant to the strong interaction. CERN notes that quarks come in 3 colors and combine in such a way as to form colorless objects, while the Department of Energy explains that quarks and gluons are the only fundamental particles with color charge, and that the strong force acts between those charges. A neutron, like other hadrons, must be colorless overall. That does not mean color is absent inside it. It means the internal colour charges are arranged so that the total outward result is neutral. You can think of this as a deeper analogue of the neutron's electric neutrality. Electrically, the quark charges add up to 0. In terms of colour, the full bound state is also neutral, but neutrality at the level of the whole hides intense structure within. The quarks carry colour charge, the gluons carry colour charge. The internal arrangement is dynamically balanced, not blank. So the neutron is neutral in more than one way from the outside, and lively in more than one way on the inside. There is another distinction here that is easy to blur if one moves too quickly. The gluons are responsible for binding quarks inside the neutron. That is one level of the strong interaction. There is also the residual strong force that acts between protons and neutrons inside atomic nuclei. These are related, but they are not the same thing in the same direct sense. The quark-level binding inside a neutron is fundamental to the neutron's existence as a hadron. The nuclear force between neutrons and protons in a nucleus is more like a leftover effect of that deeper strong interaction, much as molecules can attract each other because of the underlying electromagnetic behaviour of atoms. This matters because it keeps us from mixing two stories together. When we ask what holds the neutron together inside itself, the answer is gluons and colour charge at the quark level. When we ask what helps hold nuclei together, we're talking about a derived force between nucleons. One of the most remarkable properties of this gluon-mediated interaction is confinement. Quarks and gluons are not observed in isolation under ordinary conditions. Jefferson Lab states this plainly, noting that quarks and gluons must remain confined within protons and nuclei, and the Department of Energy says the strong force makes them extremely difficult to separate. Brookhaven adds the key contrast that although quarks move around inside protons and neutrons, free quarks are not found in nature in the usual sense. That phrase, move around inside, is important because confinement does not mean the quarks are frozen in place, like museum artifacts behind velvet ropes. They are dynamic. They carry momentum. They exchange gluons. They are active participants in a quantum system. What confinement means is that the system does not let you extract one quark cleanly and leave the rest behind as if you had removed a grape from a fruit bowl. The energy cost of separation grows in such a way that, when you push hard enough, the outcome is not a solitary liberated quark, but the creation of new hadrons. Nature does not hand you a single quark for your trouble. It gives you a different collection of bound states, and politely suggests that you have not understood the house rules. This is one of those moments where the strong force behaves almost opposite to what common sense expects. In many everyday situations, the farther apart two things are, the weaker their link becomes. The strong interaction between quarks does not reward that intuition. At short distances, quarks can behave almost as though they are relatively free inside the nucleon, which is one of the strange and well-established results of quantum chromodynamics. Jefferson Lab describes this by saying that short-distance behaviour is successfully described in terms of quarks and gluons, while large-distance behaviour is dominated by confinement. Brookhaven makes the same point in a more public-facing way when it notes the apparent discrepancy between quark confinement and their relative freedom of motion within protons. This means the neutron's interior is not a simple prison with rigid walls. It is more subtle than that. At very short ranges, quarks can move within the hadron's interior, but they cannot escape the overall bound state. The system is permissive locally and unforgiving globally. If that sounds like an oddly specific workplace policy, that may be because particle physics often discovers arrangements that would be disastrous in office management, but are excellent for matter. The quarks are not locked motionless. They are energetic and mobile within a deeply confining framework. Gluons also matter for a reason that is easy to miss if one thinks only in terms of holding things together. They contribute enormously to what the neutron is made of in the inertial sense. The Department of Energy states that the interaction between quarks and gluons is responsible for almost all the perceived mass of protons and neutrons, and Brookhaven explains that the proton's total mass is far larger than the simple sum of the masses of its constituent particles. Because the neutron is a nucleon alongside the proton, the same broad lesson applies here. The bulk of the neutron's mass comes not from adding up a few tiny bare quark masses, but from the energy stored in quark motion and gluon-mediated interactions. That fact alone should permanently cure the idea that gluons are merely connectors. They are not tiny staples. Their fields and interactions contribute to the energy budget that gives ordinary matter most of its mass. Jefferson Lab's electron-ion collider science material goes even further and emphasizes that measuring gluon fields helps explain how gluons contribute to building the bulk of visible matter in the universe today. So inside the neutron, gluons are doing at least three major jobs at once. They mediate the strong force between quarks, they interact with one another, making the internal dynamics much more complex than a simple one-messenger model. And they contribute substantially to the energy that becomes the neutron's mass. That is quite a lot for particles with no electric charge and no public relations department. There is also the matter of the gluon sea. High-energy experiments have shown that protons and neutrons are not just three valence quarks with occasional tidying up. Brookhaven and Jefferson Lab both describe nucleons as containing valence quarks, a sea of gluons, and sea-quark pairs. The gluons are not a sparse background feature. They form a dense and changing part of the interior landscape. Brookhaven notes that gluon number density increases with energy, and Jefferson Lab describes gluons as flitting in and out, multiplying and recombining. This helps explain why the neutron cannot be pictured adequately as three quarks, joined by occasional exchanges. The exchanges are not occasional in any everyday sense. The interior is saturated with field activity. Gluons are abundant. They can split, recombine, and help generate quark-antiquark pairs as part of the quantum vacuum structure inside the hadron. The neutron is therefore less like a three-bead necklace, and more like a compact, highly regulated traffic system in which the main roads, side streets, maintenance crews, and power lines are all being rebuilt at once without ever shutting the city down. It is not calm, it is stable. There is even a state of matter in which quarks and gluons are no longer confined inside individual protons and neutrons. The Department of Energy explains that if temperature and density become high enough, protons and neutrons can melt into quark-gluon plasma, a state that filled the universe shortly after the Big Bang and is now studied in collider experiments. CERN likewise describes quark-gluon plasma in heavy ion collisions as a hot and dense state associated with the early universe. That does not happen inside an ordinary neutron sitting quietly in matter around us. But the existence of quark-gluon plasma is an important clue. It tells us that confinement is not some eternal metaphysical rule detached from physical conditions. It is the behaviour of quarks and gluons under the temperatures and densities that normally prevail in hadronic matter. Push the system hard enough, and the usual boundaries dissolve. In that sense, gluons do not just bind quarks inside neutrons. They also participate in the conditions under which the entire notion of a separate neutron can temporarily disappear. For our purposes, though, the main point is simpler. The neutron stays together because gluons mediate the strong interaction among its quarks, because those gluons themselves interact, and because the resulting colour field dynamics enforce confinement. This is not a decorative detail. It is the central machinery of the neutron's interior. Without gluons, there is no strong binding of quarks into a neutron. Without gluon self-interaction, the whole character of quantum chromodynamics would be different. Without the energy of the gluon field, the neutron would not have anything like its familiar mass. That is why physicists often talk about glue when describing visible matter. The phrase sounds informal, but the idea behind it is exact enough. Gluons are the carriers of the force that binds quarks into hadrons, and their fields help generate the bulk of the matter we know. The walls around you, the metal in a key, the atoms in your hands, the nuclei in your body, all owe their durable existence not just to quarks but to gluonic binding and energy. The neutron, quiet as it may appear from the outside, is held together by some of the strongest fields in nature. Jefferson Lab says as much when it describes gluon fields as the strongest fields found in nature and links their measurement to understanding how visible matter is built. And once that is clear, another question comes into focus. If gluons are the carriers of the strong force, and if confinement is what stops quarks from escaping, why does the force behave in that peculiar way where quarks can move relatively freely at short distances but become impossible to isolate when you try to pull them apart? That odd combination is one of the defining features of the neutron's interior, and it deserves a slower look because it is where the strong force starts to feel less like ordinary sticking power and more like a rulebook written in a very different language. The title of this part hides a small trap, and it is worth stepping around it carefully before we go any further. In everyday language, saying that a force grows stronger up close sounds straightforward. Gravity feels stronger when you are near a planet than when you are far from it. The attraction of a magnet is more noticeable when you bring it nearer to a piece of metal, so one might expect the strong force to behave in that same familiar way. But the strong force between quarks is more peculiar than that. In the broad everyday sense, yes, the strong interaction is the dominant force at the tiny scales inside protons and neutrons. It is the reason those particles exist at all. But in the more precise language of quantum chromodynamics, the theory of quarks and gluons, quarks interact more weakly when they are extremely close together, and the restoring force becomes harder to escape as you try to separate them. CERN explains this as asymptotic freedom, meaning the interaction strength decreases at high energies or short distances, while Jefferson Lab describes the opposite low-energy behaviour as confinement. That combination sounds almost mischievous the first time you hear it. Weak at very short distances, strong when pulled apart. One could be forgiven for thinking the force is simply being contrary for sport. But this strange behaviour is one of the defining achievements of modern particle physics, not a poetic exaggeration. As CERN notes, the discovery of asymptotic freedom in the early 1970s laid the foundations of quantum chromodynamics, and it was important enough to be recognised with the Nobel Prize. Jefferson Lab describes the same idea in practical terms by noting that at high energies, which correspond to probing very short distances, quarks interact weakly enough that experiments can often describe what they see in terms of quarks and gluons directly. At low energies and larger effective distances, that description gives way to confinement and the visible world of hadrons such as protons and neutrons. It helps to picture the neutron less as a bag full of marbles and more as a system whose internal rules depend on scale. When the quarks are very close together inside that tiny region, they can behave in a way that is almost loose by the standards of the strong interaction. That does not mean they are free in the ordinary sense. No one is strolling casually out of the neutron and taking the afternoon off. It means that at very short separations the coupling is weaker, which is why high-energy scattering experiments can sometimes treat quarks as nearly independent during the instant of the probe. But as soon as you try to separate them over larger distances, the interaction no longer lets you continue in the same carefree way. Fermilab summarizes this elegantly by saying that quarks are weakly bound at small separations, but feel an increasingly strong restoring force at large separations. That is the odd but central rule of the game. Why would nature arrange things this way? The short answer is gluons. More precisely, it is the fact that gluons carry colour charge, and therefore interact with one another, unlike photons in ordinary electromagnetism. CERN Courier states this directly, saying that the self-interaction of the gluons leads to asymptotic freedom. Jefferson Lab likewise points to gluon self-interaction as one of the basic ingredients behind confinement, while noting that quark confinement is still not fully understood in a complete intuitive sense, even though the overall phenomenon is well supported by theory and experiment. This self-interaction is what makes quantum chromodynamics behave so differently from the forces that fit more comfortably into everyday analogy. If photons behave the way gluons do, introductory electricity lessons would be even less restful than they already are. In electromagnetism, the field around a charged particle is altered by the virtual particles of the vacuum in a way that tends to screen the charge. In quantum chromodynamics, the gluon field contributes an opposite effect, often called anti-screening. The Nobel lecture by David Gross describes asymptotic freedom as arising because the anti-screening from gluons overcomes the screening from quarks. That is an abstract sentence until one translates it into behaviour. What it means in practice is that when you probe quarks at very short distances, the effective interaction can become smaller. When you try to separate colour charges over larger distances, the field does not spread out and fade away in the familiar manner of ordinary electric fields. Instead, the interaction remains intense enough that isolation never becomes the easy option. That is one of the deep consequences of gluons being active participants rather than passive messengers. This is also where the language of distance can become a little slippery, so it is worth being careful. When people say the strong force grows stronger with distance inside hadrons, they do not mean it keeps increasing forever in a naive mechanical way like a spring pulled to cosmic length. In the neutron, once you try to pump enough energy into separating quarks, the energy stored in the gluon field can turn into new quark-antiquark pairs. Fermilab explains that before the separation becomes macroscopic, the gluon field sparks into additional pairs, which is why freely propagating quarks are not observed in nature. Instead of one lonely quark escaping, the system reorganizes into new hadrons. In other words, the neutron does not break open the way a container does. It rearranges itself into other bound states. If you insist on pulling harder, nature does not surrender a quark. It sends you more hadrons and, in its own silent fashion, suggests that you may not be asking the right kind of question. There is something almost paradoxical in this. The quarks inside a neutron can act nearly free when examined in a high-energy collision, yet no quark is ever seen drifting alone out in the detector like a lost shopping cart in a parking lot. That tension between relative freedom and absolute confinement was one of the great clues that guided particle physics toward quantum chromodynamics. Jefferson Lab describes this split clearly. At high energies and short distances, quarks interact very weakly and can be treated as partons in scattering. At low energies and distances comparable to the size of hadrons, confinement dominates, and the efficient description is no longer in terms of free quarks, but in terms of complete hadrons. This dual character is not an inconsistency. It is the signature of how the strong interaction runs with scale. The theory changes its practical face depending on how closely you look and how hard you hit the system. That running with scale is one of the most important ideas in modern physics. A force is not always one fixed strength under every circumstance. Its effective strength can depend on the energy of the process, or, loosely speaking, on how finely you probe the system. Quantum chromodynamics is the famous case where the coupling becomes smaller at shorter distances. CERN states this directly in its account of asymptotic freedom, and CERN Courier notes that the gauge coupling of quantum chromodynamics decreases when the energy is increased. The closer and harder the probe, the more the quarks can appear almost free for that brief interaction. The larger the distance scale relevant to the hadron, the more confinement takes over. This is why the inside of a neutron cannot be understood with one single simple picture. At one scale it looks like a system of partons sharing momentum. At another it looks like an indivisible neutron. Both descriptions are useful, but they belong to different experimental questions. The phrase very small room from the previous section now takes on a sharper meaning. It is not just that the room is tiny, it is that the room has unusual rules. If 3 people are put in a normal small room, being close together usually increases their immediate interaction, and moving apart reduces it. Inside the neutron, the quarks occupy a region where closeness does not translate into the simple classical increase one might expect. Instead, the quantum field behavior of the strong interaction produces this strange regime in which the shortest range behavior can be comparatively weak, while separation triggers a stronger restoring tendency. This is not because the quarks have changed their minds. It is because the vacuum and the gluon field are part of the system. The room is active, the room pushes back. Jefferson Lab emphasizes that the strong force is the attraction felt by quarks when they share colors via gluons, and because gluons themselves carry color, they also interact among themselves. That self-interaction is not a side detail. It is the reason the room behaves unlike any ordinary room you've ever been in, including those conference venues where the coffee is weak and the acoustics are somehow both echoing and muffled at once. This is also where one must be careful not to mix up two different uses of the phrase strong force. Inside the neutron, we are talking about the fundamental color force that binds quarks through gluons. At the level of whole protons and neutrons inside an atomic nucleus, one often speaks of the strong nuclear force that binds nucleons together. That nuclear force is related, but it is not the same thing in the same direct way. It is more like a residual effect of the deeper quark and gluon dynamics. So when we say the force grows harder to escape as quarks are separated, we are talking about the more fundamental level inside the hadron itself. This distinction matters, because otherwise one might imagine that the same rule applies identically to every situation involving nuclear matter, and physics becomes confusing enough without our help. CERN draws the distinction by describing quantum chromodynamics as the force that holds quarks and gluons together in hadrons, and also, in a related way, protons and neutrons together in nuclei. The deeper lesson here is that the neutron is not built from quarks first and then glued together second in some chronological sense. The quarks and gluon field form one system, and the way the force changes with scale is part of what makes that system possible. If the strong coupling stayed weak at large distances, quarks would not remain confined in hadrons. If it stayed equally strong at the shortest distances, the successful high-energy description in terms of partons would fail. The peculiar blend of asymptotic freedom and confinement is not an awkward compromise. It is the reason visible matter can have both internal structure and external stability. The neutron can be probed deeply enough to reveal quarks, yet it still persists as a neutron in the ordinary world because those quarks cannot be peeled away one by one. CERN and Jefferson Lab both present this two-sided behavior as a hallmark of quantum chromodynamics. There is another consequence of this behavior that deserves attention because it reaches beyond the question of binding. The same gluon dynamics that produce confinement also contribute heavily to the mass and structure of nucleons. The Department of Energy explains that the interaction between quarks and gluons is responsible for almost all the perceived mass of protons and neutrons. So the force is not simply a jailer preventing escape, it is part of what gives the neutron its very substance. The kinetic motion of quarks, the energy of gluon fields, and the collective structure of the bound state account for far more of the neutron's mass than the tiny bare masses of its valence quarks alone. This means that when we ask why the strong force behaves as it does, we are also asking why ordinary matter is as heavy and as durable as it is. Even with all of this in hand, there is still a note of honesty physics must keep. Quark confinement is experimentally supported and built into the successful framework of quantum chromodynamics. But a simple everyday proof with the comfort of a school geometry exercise is not what we have. CERN Courier explicitly notes that a rigorous proof of confinement is still missing, even though the overall picture is deeply established. This is one of those healthy scientific situations where the theory works extraordinarily well. The experiments line up, the consequences are everywhere, and yet some of the deepest mathematical understanding remains incomplete. That is not a sign of weakness. It is a reminder that nature often lets us use truths successfully before it allows us to phrase them in the most satisfying possible way. So if we answer the title question carefully, the reply goes like this. The strong interaction does not simply grow stronger the closer quarks are brought together. In fact, at the shortest distances, quarks interact more weakly. What makes the force so strange and so important is that trying to separate colour charges does not make the interaction fade away, as ordinary intuition would suggest. Because of gluon self-interaction and the running of the strong coupling, the effective interaction leads to confinement at larger scales inside hadrons, while asymptotic freedom governs the shortest scales. That combination is what holds the neutron together without making its quarks easy to isolate. Once that point settles in, the neutron starts to look even less like a simple trio of particles, and more like a crowded and changing interior landscape. The valence quarks are still essential, but the force that binds them is so active that it fills the neutron with more than just those three named occupants. Gluons are being exchanged. Quark-antiquark pairs can flicker into existence and disappear. Momentum is shared in ways that are far from static. In other words, once the strong interaction is understood as a dynamic field rather than a fixed bond, it becomes much easier to see why the neutron contains not just three quarks in a cramped arrangement, but a restless quantum sea beneath the calm exterior. If the neutron were really nothing more than three quarks packed into a tiny volume, then the story would already be complicated enough. But that picture, while useful, is still too spare. Modern particle physics says the neutron contains three valence quarks that define its identity, one up quark and two down quarks, but it also contains a quark-gluon sea made of gluons and short-lived quark-antiquark pairs that continuously appear and disappear. The Department of Energy describes these additional quarks as sea quarks that constantly pop in and out of existence inside protons and neutrons, while Jefferson Lab describes protons and neutrons as three valence quarks held together by gluons along with a quark-gluon sea of particles that constantly pop into and out of existence. That matters because the phrase three quarks can trick the mind into imagining a fixed inventory, as though the neutron were a cabinet with exactly three items inside and no room for anything else. In reality, the interior is a dynamic quantum system. The valence quarks are essential, but they are not alone. Gluons are constantly being exchanged, and those gluons can in turn produce quark-antiquark pairs. Brookhaven explains this clearly when describing the internal microcosm of a nucleon, noting that the gluons keep producing quarks and antiquark pairs called sea quarks. The result is that the neutron is not a quiet arrangement of three permanent objects. It is a crowded bound state in which the defining quarks live inside a constantly shifting environment created by the strong interaction. This sea is not decorative. It changes how momentum is shared inside the neutron. A simple first guess might be that the three valence quarks carry all of the neutron's momentum. Jefferson Lab lecture material explains that this is not what experiments show. Instead, at least about half of the nucleon's momentum is carried by something besides the three valence quarks, and the missing share belongs to gluons and virtual quark-antiquark pairs. That is one reason physicists moved away from the old image of nucleons as little trios of particles and toward the modern language of partons, meaning the quarks and gluons that collectively share the momentum revealed in high-energy scattering experiments. The neutron's interior is not just populated, it is busy in a measurable way. CERN made the same point in a more recent way when discussing how nuclei are probed at the Large Hadron Collider. Its summary notes that the common picture of nucleons as three quarks is incomplete, because a complex sea of quark-antiquark pairs and gluons makes up a large fraction of the proton and neutron energies. That wording is useful because it reminds us that energy is not some side accounting detail. In particle physics, energy is part of what gives an object its inertia, its structure, and many of its observable properties. So when physicists say the neutron contains a sea, they do not mean a few optional extras drifting around the edges. They mean that a large share of the neutron's internal energy and momentum belongs to this dynamic background of gluons and transient quark pairs. At this point, it helps to be careful with the word virtual, because it can sound like a polite way of saying unreal. In particle physics, it means something more specific and more interesting. These short-lived quark-antiquark pairs are not free particles flying around independently inside the neutron like birds in a greenhouse. They are transient features of the quantum fields inside the bound state. Jefferson Lab describes them as virtual quark-antiquark pairs in the nucleon sea and notes that they exist only briefly, while the lab's public explanation of future collider science says these transient sea particles continuously blink into and out of existence inside hadrons. so the sea is real as part of the neutron structure, even though the individual pairs are fleeting. The activity is not permanent at the level of each pair, but it is permanent at the level of the overall system. This is one of the reasons the neutron is hard to visualize honestly. In ordinary objects, the main constituents are usually the stable ones. A chair is mostly wood, metal, foam, and fabric, not a continuous froth of briefly appearing ingredients. The neutron is different. Its defining valence quarks persist as the core identity, but the strong force is so intense that it fills the interior with additional activity all the time. Jefferson Lab describes the force between quarks as carried by gluons through color charge, and Brookhaven describes the interior of the nucleon as abundantly full because gluons produce more quark-antiquark pairs. So the restless sea is not a complication added after the fact, by theorists trying to make their subject sound difficult. It is the natural consequence of how strongly interacting quantum fields behave in a tightly confined region. There is also a practical reason physicists talk so much about the sea. Many of the neutron's measurable properties cannot be explained by valence quarks alone. Spin is a major example. Brookhaven's discussion of neutron spin states that the spins of the three main valence quarks account for only about 1/4 to 1/3 of a neutron's total spin, and that gluons, sea antiquarks, and orbital motion also matter. That is a striking result because it means the familiar 1 up and 2 down picture, though necessary, is nowhere near sufficient if you want to explain how the neutron behaves as a whole. The sea contributes not only to the neutron's momentum and energy, but also to its angular momentum story, which is one reason neutron structure remains an active field of research rather than a completed chapter in physics history. The same broad lesson appears in proton studies, which often provide much of the experimental foundation because free protons are easier to work with than free neutrons. The Department of Energy describes the proton as an ocean of shifting quarks and gluons, adding that gluons rapidly split into short-lived pairs of quarks and antiquarks called sea quarks. Brookhaven's public material on the electron-ion collider makes a similar point when it speaks of the ocean of gluons and the sea of quark-antiquark pairs formed when gluons interact. Since protons and neutrons are sibling nucleons built from the same light quark flavors and the same strong interaction, that picture is central to understanding both, even though the exact distributions are not identical. The neutron is therefore best thought of not as a special exception, but as one member of a family whose internal sea is a fundamental feature. The word sea can also make the interior sound smooth and featureless, which is not quite right either. Physicists are interested in how the sea is distributed in momentum, in position, in flavor, and in spin. Jefferson Lab says an electron-ion collider could reveal how quarks and gluons are distributed inside hadrons, how they move, and what role the sea plays in microscopic structure. Brookhaven says the same machine is designed to take three-dimensional precision snapshots of the internal structure of protons and nuclei, and to map the distribution and movement of the sea and the gluon ocean. This tells us something important about the current state of knowledge. The existence of the sea is not in doubt. The open questions concern its detailed geography. How much of the neutron's momentum sits in gluons under different conditions? How are the sea quarks distributed? How do they contribute to spin and shape? Those are the live questions now. One especially interesting aspect of the sea is flavor. Gluons can produce different kinds of quark-antiquark pairs, including not only up and down pairs, but under the right conditions, strange quarks as well. Jefferson Lab's summary of the G0 experiment explains that strange quarks are thought to appear in the proton sea as virtual particles, and that researchers designed experiments to measure what effect these temporary residents have. The same article emphasizes that protons and neutrons are unusual, because most of their mass comes from strong interaction energy and quark motion rather than from the bare masses of the matter constituents. That means even heavier flavors that appear only briefly can still leave detectable traces in the neutron's properties, such as its magnetism or charge distribution, without becoming permanent residents in the way the valence quarks are. This is also where the neutron's electric neutrality becomes a little more subtle than the simple textbook version. The valence quark charges add to zero, yes, but the neutron's internal charge distribution is not uniform or blank. Because the quarks and C particles are moving and fluctuating, different regions inside the neutron can carry different effective distributions of charge, even though the total adds to zero. Experiments that probe form factors and related observables are sensitive to that internal arrangement. Jefferson Lab frames this broader program as an effort to understand how charge and magnetism are distributed in nucleons, and how the underlying quarks and gluons occupy momentum and space. So a neutral neutron does not mean there is no internal electrical structure. It means the positive and negative contributions, including those from the C, balance in the end. Another reason the C matters is that it connects the neutron to the early universe in a surprisingly direct way. Under ordinary conditions, the C exists inside a confined hadron. In the first moments after the Big Bang, and in heavy ion collisions today, quarks and gluons can exist in a much less confined state known as quark-gluon plasma. The Department of Energy notes that just after the Big Bang there were no protons and neutrons yet, only a sea of quarks and gluons, while Brookhaven and CERN both study how that hot early state relates to the later emergence of confined matter. This does not mean the neutron is a tiny patch of early universe trapped forever in miniature, but it does mean that the restless sea inside the neutron is a local, bound, cooled descendant of the same strong interaction physics that once governed the whole cosmos. Of course, learning any of this about the neutron is experimentally awkward, because neutrons do not sit around alone for long. Brookhaven notes that neutrons do not exist by themselves for long in nature, which makes their properties harder to measure than those of protons. That is why neutron structure is often inferred through scattering on light nuclei such as helium-3 or deuterium, where one can isolate neutron information indirectly. The Department of Energy likewise explains that scattering experiments with polarized beams and targets reveal how quarks and gluons contribute to nucleon properties. So the restless sea inside the neutron is not something scientists have watched directly with a tiny internal camera. It is something they reconstruct from how the neutron responds when struck, how momentum is distributed among partons, and how the observed data fit the framework of quantum chromodynamics. When all of this is put together, the neutron begins to look less like a compact object with a few named contents, and more like a stable pattern emerging from an active quantum interior. It has 3 valence quarks. Yes, but those quarks move inside a sea of gluons and transient quark-antiquark pairs. That sea carries a large share of the neutron's energy and momentum, contributes to its spin, influences its charge and magnetism, and makes the particle's internal structure much richer than the old picture allowed. Jefferson Lab says directly that the role of this quark-gluon sea in protons and neutrons remains one of the major things future experiments are meant to reveal in detail, and Brookhaven says the same about mapping this internal ocean. The calm exterior of the neutron is therefore not a sign of simplicity. It is the outward stability of a system whose interior never really sits still. And once you accept that the neutron contains not just fixed valence quarks, but an active sea whose motion and fluctuations help determine the particle's real properties, it becomes much easier to see why questions about spin, magnetism, shape, and internal charge distribution are so hard to answer with simple diagrams. The neutron is not just made of matter, it is made of organized motion, shared momentum, and a crowded field of interactions that leave their mark on everything the particle is observed to be. One of the easiest ways to make the neutron sound more familiar than it really is to use the word spin too casually. The word arrives with a built-in image. It suggests a tiny object turning around like a top, perhaps very quickly, perhaps with admirable commitment, but still in a way our ordinary minds can picture. That is not what physicists mean. In modern particle physics, spin is an intrinsic form of angular momentum. It is one of the neutron's basic quantum properties, and it exists whether or not the neutron is moving through space in any obvious way. The Department of Energy describes the spin of the proton as intrinsic angular momentum, and Jefferson Lab makes the same broader point for the nucleon family, adding that a nucleon's total spin does not come only from the spin of its constituent quarks, but also from the quark's orbital angular momentum and the gluon's angular momentum. Since the neutron is a nucleon alongside the proton, the same structural lesson applies here. The neutron's spin is real, measurable and essential, but it is not the kind of spin that would make sense if you tried to draw a tiny ball with an arrow on it and call the matter settled. That matters because spin is tied to several of the neutron's outward properties. The Department of Energy notes that spin is among the proton's most basic properties, and that its direction and strength affect magnetic and electrical behaviour as well as internal structure. Again, the neutron belongs to the same nucleon family and is studied in the same framework of quarks and gluons, so this connection between spin and structure is not a side remark. It is one of the reasons spin has occupied so much experimental attention for decades. The old hope was that a neutron's overall spin might simply be the sum of the spins of its three valence quarks. Jefferson Lab says directly that this is not the full story for nucleons, and CERN's long-running discussion of the spin puzzle says the same. The quark spins contribute only part of the total. Gluons matter, orbital motion matters, the C matters. A neutron is not a quiet object with a single internal source of angular momentum. It is a bound quantum system in which several kinds of motion and several kinds of constituent activity combine to produce the final spin one observes. That is why the word spin, simple as it sounds, opens a much deeper question than the first diagram in a textbook would suggest. There is something revealing in the fact that spin can change the way physicists think about a particle's structure in the first place. If the neutron were just a little neutral bead, spin would be one more label attached to it and not much else. But the Department of Energy explains that changing a proton's spin alters its structure, and Jefferson Lab's work on generalized parton distributions says one of its central goals is to build a detailed three-dimensional picture of the nucleon in terms of quarks and gluons, and to understand how that complex structure leads to familiar properties such as mass, spin, and magnetic moment. A recent Department of Energy summary on imaging proton interiors adds that future precision measurements are meant to reveal how the transverse motion of quarks and gluons contributes to overall spin. Put those statements together, and a more careful picture emerges. Spin is not just a property carried by the neutron. Spin is also a useful axis relative to which internal motion can be organised and measured. Once you choose a spin direction, questions about distribution, asymmetry, and internal distortion become meaningful. In that sense, the neutron's spin does not merely sit on top of the structure. It helps define how the structure is described. This is where charge enters the story in a more subtle way than the word neutral might lead you to expect. The neutron has no net electric charge. That much is correct, and it is one of the first things anyone learns about it. But Jefferson Lab's neutron charge distribution program states that the neutron's electric form factor carries vital information about the origin of charge distribution in the neutron, while older Jefferson Lab material on neutron electromagnetic form factors explains that understanding nucleon form factors means understanding the distribution of charge and magnetization within nucleons. Those statements would make no sense if neutrality meant blankness. A net charge of 0 does not mean every part of the neutron is electrically featureless. It means the positive and negative contributions balance overall. Inside the neutron sit charged quarks, one up quark and two down quarks, and within the C there are additional fluctuating charged pairs. Their distribution in space and momentum is not trivial. The total comes out to 0, but the internal electrical arrangement is structured enough that physicists can measure a non-zero electric form factor and use it to infer how charge is arranged within a particle that, from a distance, appears neutral. That internal electrical structure becomes even more convincing once magnetism enters the discussion. A neutron has no net electric charge, yet it has a magnetic moment, and that magnetic moment has been measured very precisely. The official NISTCA data page lists a non-zero neutron magnetic moment, and Jefferson Labs' neutron electromagnetic structure program treats the neutron electric and magnetic form factors as core observables for understanding nucleon structure. That combination of facts is one of the strongest plain language signs that the neutron is composite rather than elementary. A neutral object with no internal charge structure would not naturally present the kind of magnetic behaviour the neutron does. The best explanation is the one modern particle physics provides. The neutron contains charged quarks moving within a bound system, with spin and orbital motion contributing to its magnetic properties. So although the neutron does not interact electrically in the blunt direct way a proton does, it is not magnetically silent. The internal motion of charge still leaves a measurable fingerprint. It is one more case where the outward neutrality of the neutron hides a very active interior. Now we can turn to the word shape, which is perhaps the most treacherous word in this whole section, because it tries to make a quantum object sound like a fruit. Ask for the shape of an apple and the question is obvious. Ask for the shape of a neutron, and the answer depends entirely on what you mean. Jefferson Labs says its generalized parton distribution program aims at a detailed three-dimensional picture of the nucleon in terms of quarks and gluons, while another Department of Energy article explains that precise imaging will reveal the transverse motion of quarks and gluons inside a proton relative to its spin axis. That is already enough to tell us that shape, at this level, does not mean a hard shell with a fixed edge. It means distributions, charge distribution, magnetization distribution, momentum distribution, spatial probability relative to a chosen axis. A neutron is not a tiny rigid bead with a painted boundary. It is a quantum object whose internal constituents are distributed in ways that can be mapped statistically and whose appearance depends on which property you're trying to image. When physicists argue about nucleon shape, they're usually not asking whether it is literally a miniature sphere floating in empty space. They're asking how internal charge, magnetization and parton distributions are arranged, and whether those arrangements stay symmetric or become distorted when spin and motion are taken into account. This is where the strange shape of the neutron becomes a serious question rather than a decorative phrase. In ordinary life, shape is something an object has all at once, from every angle, whether or not you're paying attention to it. In the neutron, shape can depend on what quantity you probe and whether the particle is polarized, meaning whether its spin direction has been selected rather than averaged over. A Jefferson Lab theory talk frames one of the key open questions exactly this way, asking how hadron spin influences the spatial distribution of partons and whether polarization leads to deformation of the internal distribution. The Department of Energy's recent imaging summary likewise ties proton spin to the transverse motion of quarks and gluons, meaning that once spin is specified, the internal cloud of constituents need not look the same in every direction. So the strange shape of a particle is not necessarily a matter of having a lopsided outer surface. It can mean that the internal distribution of quarks and gluons is anisotropic, organised differently along and across the spin axis, or distorted once orbital motion and spin-dependent correlations are included. What looks nicely averaged and round in one description can reveal a more complicated internal pattern in another. This also helps explain why spin, charge, and shape belong together, rather than feeling like three unrelated topics forced into the same room. Spin sets a preferred direction. Charge and magnetization provide measurable distributions. The quarks and gluons inside the neutron respond to the strong interaction, while carrying momentum and angular momentum in ways that need not be spherically innocent. Jefferson Lab says generalized parton distributions connect the nucleon's quark and gluon constituents to familiar properties like mass, spin, and magnetic moment, and that the feasibility of accessing quark orbital angular momentum experimentally has been demonstrated in this framework. That is an important bridge. Orbital motion is one of the things that can make a quantum system's internal distribution depart from the simplest spherical expectation. The neutron's shape in the modern sense is therefore not something added after the spin puzzle is solved. It is part of the same puzzle. If spin is built from quark spin, gluon angular momentum, and orbital motion, then the way constituents move in 3 dimensions is directly tied to the way the neutron acquires its overall angular momentum. Shape is not decoration. Shape is evidence about motion. There is an amusing irony in all this. The neutron was once introduced as the plain one, neutral, heavy, useful, and perhaps a little reserved. Yet once physicists began measuring its electromagnetic form factors and spin-dependent behaviour, the supposedly plain particle turned out to have a non-zero magnetic moment, a measurable internal charge distribution despite total neutrality, and a structure whose detailed 3-dimensional description depends on how quarks and gluons move relative to spin. Jefferson Lab notes that precise determination of the neutron electric form factor was difficult for decades because there is no free neutron target and because the charge form factor is so small, but those very difficulties are part of what make the results so meaningful. A non-trivial charge structure in a neutral particle is not the sort of thing one shrugs off as administrative detail. It is direct evidence that the neutrons inside cannot be reduced to a featureless average. The same goes for its spin structure. Jefferson Lab says clearly that how quarks spin, orbital motion, and gluon angular momentum add up to the nucleon's total spin remains unclear. So the neutron is not just a solved object with a few decorative complications. It is a stable particle whose most familiar labels conceal an astonishing amount of unresolved internal detail. If there is a good way to hold all of this in mind at once, it is this. Spin tells you the neutron is a quantum object with intrinsic angular momentum, not a little spinning bead. Charge tells you that net neutrality does not erase internal electrical structure. Shape tells you that a composite quantum particle is described by distributions rather than by a hard surface, and those distributions can depend on spin, motion, and the strong interaction in subtle ways. The neutron is therefore quiet only from a distance. Up close, it is a system whose magnetism, internal charge balance, and 3-dimensional quark and gluon structure are all tied together. And once those pieces are on the table, the next question comes almost naturally, because if the neutron's outward properties depend so heavily on internal motion and strong interaction energy, then we have arrived right beside one of the most important issues of all, namely where the neutron's mass actually comes from. By the time most of us first hear the word mass in science, it already sounds settled. Mass is how much matter something has. It is what makes a stone heavy, a chair difficult to carry upstairs, and a sleepy person regret buying the larger suitcase. Then the neutron arrives, and that comfortable picture begins to wobble. If you ask where the neutron's mass really comes from, the answer is not simply that it comes from the masses of the quarks inside it. In fact, that answer is badly incomplete. The Department of Energy states that the interaction between quarks and gluons is responsible for almost all the perceived mass of protons and neutrons, while Brookhaven says that quarks are nearly massless, gluons are massless, and yet their interactions generate the energy that gives mass to visible matter. That is the central surprise here. The neutron is heavy on the particle scale not because it contains a few especially heavy ingredients, but because the strong interaction inside it stores and organises enormous energy. This is one of those moments where physics gently asks us to let go of a habit of thought that works perfectly well for fruit bowls and boxes of books. In ordinary life, if you want to know the mass of a collection of things, you add the masses of the things. If 3 objects go into a bag, the bag weighs roughly what those 3 objects weigh together, allowing for the possibility that someone has hidden a brick in the bottom. But the neutron is not like that. It is not a bag containing 3 quarks whose masses simply add up to the final total. Brookhaven explains that the quarks account for no more than a tiny fraction of a proton's total mass, and that the Higgs field plays essentially no role in the masses of protons and neutrons, while the Department of Energy explains more generally that quark and gluon interactions account for almost all the mass of protons and neutrons. Since the neutron is a nucleon built from the same light quark flavours and the same strong interaction, the lesson is the same. The mass is mostly emergent. It comes from the energy of the bound system. That word emergent is important because it prevents a very common misunderstanding. When people hear that the Higgs field gives particles mass, they sometimes assume that this must explain the mass of everything straightforwardly, including the neutron in nearly its entirety. The real story is subtler. The Higgs mechanism does give the elementary quarks their bare masses, and without that contribution the details of the neutron would not be what they are. But those bare quark masses are only a small part of the neutron's final mass. Brookhaven says this directly in plain language, noting that the Higgs plays essentially no role in the masses of protons and neutrons compared with the strong interaction. CERN's overview of the Higgs mechanism explains that the Higgs field gives mass to fundamental particles, which is true, but that does not mean it directly accounts for the bulk of the mass of composite hadrons like neutrons. Most of the neutron's mass is generated dynamically inside quantum chromodynamics, the theory of quarks and gluons. So where does that mass come from, if not mainly from the quark's own tiny bare masses? It comes from motion, confinement, field energy, and the restless activity of quarks and gluons inside the neutron. Brookhaven's electron-ion collider science summary says that the interactions of nearly massless quarks and massless gluons are sufficiently strong to generate the energy that gives mass to matter. The Department of Energy says the same in broad terms when it identifies quark and gluon interaction as the source of almost all the perceived mass of protons and neutrons. This means the neutron's mass is largely the mass equivalent of energy trapped in a very small region by the strongest force in nature. The quarks are moving, the gluon fields are active. The sea of quark-antiquark pairs contributes to the internal dynamics. All of that energy counts. The neutron is, in a very real sense, heavy because its interior is busy. There is something almost philosophical in that result, though physics reaches it by hard calculation rather than by sitting in a garden looking reflective. The neutron teaches that mass is not always best understood as a pile of ingredients. Sometimes it is better understood as a stable pattern of energy. That sounds abstract until one remembers that this pattern is what makes visible matter feel substantial. The Department of Energy says that the interaction between quarks and gluons is therefore where we get our mass, meaning not just the mass of isolated neutrons and protons, but the mass of the ordinary matter built from them. Brookhaven says nearly all visible matter is made from quarks and gluons, whose interactions generate the energy that becomes mass. So the weight of everyday objects comes mostly from the energy of the strong interaction inside nucleons, not from the Higgs field acting alone and not from electrons, which contribute very little by comparison. A table feels solid and heavy because of furious invisible activity in the nucleons inside its atoms, which is not the sort of sentence that makes moving furniture any easier, but does make it more interesting. This is also why the neutron's mass is inseparable from confinement. If quarks were free particles wandering about independently, the neutron would not exist as the compact bound state we know. The strong interaction confines them to a tiny region, and that confinement itself stores energy. Brookhaven's discussion of the electron-ion collider says one of the great goals of current and future experiments is to understand how quark-gluon interactions generate the bulk of nucleon mass. While the Department of Energy states in its budget justification that the electron-ion collider will help discover how the mass of everyday objects is dynamically generated by quark and gluon fields inside protons and neutrons. The word dynamically matters here. The mass is not merely assigned. It is generated by ongoing field behavior and by the structure of the confined state. The neutron is not heavy because nature attached a label. It is heavy because the internal rules of quantum chromodynamics create a bound system with large stored energy. At this point, it is natural to ask how physicists know any of this with confidence, given that no one can open a neutron and inspect the energy bookkeeping directly. Part of the answer comes from scattering experiments that reveal how momentum and energy are shared among quarks and gluons. Part comes from lattice quantum chromodynamics, a computational approach in which the equations of the strong interaction are solved numerically on supercomputers. Brookhaven describes lattice QCD as a first principles method for investigating the strong dynamics of quantum chromodynamics, and the Department of Energy recently highlighted first principles numerical calculations that map how mass is distributed within hadrons, such as the proton. Jefferson Lab and Brookhaven both treat lattice QCD as one of the essential tools for turning the elegant but extremely difficult equations of the strong force into quantitative predictions about hadron structure. So the neutron's mass story is not a hand-waving philosophical preference for energy over substance. It is a result backed by experiment and by large-scale calculation. Even then, the mass story is not finished in every detail. Physicists know the broad answer very well. The neutron's mass comes mostly from the strong interaction, not from the sum of quark masses alone. But understanding exactly how the various contributions divide up within the full theory remains an active area of research. Jefferson Lab lecture material frames this as the question of how quantum chromodynamics generates nucleon mass, and the Department of Energy's nuclear physics planning documents list the dynamical generation of nucleon mass as a major scientific priority. Brookhaven's recent statements about the future of the electron-ion collider do the same, placing quark and gluon mass generation among the headline questions the field still aims to resolve in greater detail. That is a healthy kind of incompleteness. The foundation is known. The finer decomposition is under investigation. Physics is not unsure whether the strong interaction is the main source of neutron mass. It is working to refine exactly how that mass is distributed among quark energy, gluon energy, and related contributions in a fully controlled way. There is also an elegant consequence of all this for how we think about matter more generally. The neutron is made from light quarks, and yet it is much heavier than those quarks taken on their own. That means mass at the level of ordinary matter is not simply inherited from elementary building blocks in a passive way. It can be created by interaction. Brookhaven's public explanation makes exactly this point, when it asks where the remaining 99% of nucleon mass comes from if quarks are nearly massless and gluons are massless, then answers by pointing to the strong force. CERN's broader explanations of the Standard Model make clear that quarks and gluons are the relevant ingredients inside hadrons, while the Department of Energy identifies their interaction as the source of almost all the perceived mass of protons and neutrons. Put together, these sources tell a remarkable story. Visible matter is not heavy because its deepest constituents are themselves especially heavy. It is heavy because the rules that bind them create energetic bound states. Mass in this part of nature is something the system does. That perspective also helps explain why the neutron and proton are so central to the mass of the world despite not being elementary particles. The electron is elementary, but it contributes very little to the mass of atoms. Most of the mass sits in the nucleus, and most of the nucleus is made of protons and neutrons. Brookhaven notes that visible matter gets its mass mainly from protons and neutrons in atomic nuclei, and the Department of Energy says the interaction between quarks and gluons is therefore where we get our mass. So if someone were to ask where your mass comes from in a deep particle physics sense, the most honest answer would not begin with your muscles or bones or the food you ate last week. It would begin with quantum chromodynamics and the energy trapped inside nucleons. The neutron, once again, turns out to be one of the quiet places where the visible world gets most of its substance. There is a nice irony here. The neutron is electrically neutral, and that can make it sound like a modest supporting character. Yet when it comes to mass, it is one of the main places where the universe shows off one of its boldest tricks. Take ingredients that are light, add a massless force carrier, confine them inside a tiny region with extremely strong interactions, let the quantum fields roil with motion and exchange. Out comes a particle whose mass is mostly the energy of the system itself. Brookhaven says this directly in the language of visible matter, and the Department of Energy says the same in the language of quarks and gluons. The neutron is not heavy because it hides a secret dense nugget in its centre. It is heavy because the strong force builds substance out of activity. This is also why the neutron resists the older mechanical habit of thinking of matter as made from little solid pellets whose properties are fixed once and for all. The neutron is a bound quantum system. Its mass is not a label pasted on from outside. It emerges from the interplay of quarks, gluons, confinement, and motion. That is one reason the study of nucleon mass is still tied so closely to new facilities, new lattice computations, and new imaging techniques. The Department of Energy's recent hadron mass story highlights first principles, numerical work on how mass is distributed within hadrons, and Brookhaven's electron-ion collider program frames mass generation as one of the great unresolved frontiers. In other words, we know the broad origin, but the detailed map is still being drawn. The neutron keeps its deepest bookkeeping somewhat private. And once mass is understood in that way, as something produced by confined quarks and gluons, rather than merely inherited from a list of constituent masses, another feature of the neutron becomes much easier to appreciate. A particle whose identity depends on internal quark flavor and strong interaction structure need not be eternally stable when left on its own. The same deep rules that give the neutron its mass also allow it, in the right circumstances, to change into something else. Inside many nuclei it can remain bound and effectively stable. Outside them, it eventually decays. So after asking where the neutron's mass comes from, the next natural step is to ask why a free neutron does not last forever, and what that slow, quiet transformation reveals about the particle's internal structure and its place among the building blocks of matter. There is a certain quiet betrayal at the heart of the neutron. For long stretches of physics, we have been treating it as a resident of stability, one of the two great particles that sit in atomic nuclei and help make ordinary matter possible. That description is fair as far as it goes, but it leaves something important out. A neutron inside many nuclei can remain there indefinitely. A neutron on its own cannot. Left free, outside the support and constraints of the nucleus, it eventually decays. The National Institute of Standards and Technology describes free neutron beta decay as the transformation of a neutron into a proton, an electron, and an electron antineutrino, while the Department of Energy describes the same process as a weak interaction in which a neutron changes into a proton and creates an electron and an electron antineutrino. In other words, a free neutron does not simply sit there being itself forever. It has another allowed future, and on a timescale of about 15 minutes, it takes it. That fact matters because it tells us something deep about what the neutron really is. A neutron is not a timeless little pebble. It is a composite particle whose identity depends on a specific quark arrangement, and that arrangement is not the lowest energy option available once the neutron is free. The older NIST review of neutron beta decay explains that at the quark level, the decay is understood as the conversion of a down quark into an up quark through the weak interaction. The Department of Energy gives the same physical picture in simpler language, saying that in beta minus decay, the weak force causes a neutron to change into a proton, and that charge current weak interactions are the ones that change a quark's charge. So when a neutron falls apart, what really happens is not that the whole neutron cracks like a shell. One of its down quarks changes flavor. The neutron's internal balance shifts from 1 up and 2 down quarks to 2 up and 1 down quark, and the particle becomes a proton, while an electron and an antineutrino carry away the rest of the process. This is one of the best places to correct a very understandable but misleading mental image. The electron produced in neutron decay is not a tiny object that had been tucked inside the neutron all along, waiting politely for its cue. The NIST review explains that neutron beta decay is a weak process described at the quark level, with the final decay products emerging from the interaction itself. The continuous spread of electron energies in beta decay was one of the historical reasons Pauli proposed the neutrino, because the electron did not come out with one fixed energy, as it would have in a simple two-body breakup. Instead, the available energy is shared among the proton, the electron, and the antineutrino. So when the neutron decays, the electron is not being released from storage. It is being created in the decay process as the weak interaction reshuffles the particle content of the system. That may sound like a fine distinction, but it is exactly the kind that keeps particle physics from turning into a museum of bad analogies. The next obvious question is why the neutron is allowed to do this at all. The reason is energy. NIST's review notes that Chadwick and Goldhaber's early mass measurements were precise enough to show that the neutron is slightly heavier than the proton, and therefore it is energetically allowed for a free neutron to decay. The same review gives the relevant mass difference and the available decay energy, and it points out a crucial consequence of how small that energy release is. Because the neutron is only a little heavier than the proton, the decay has relatively little energy to distribute among its products. That small energy release is one reason the neutron's lifetime is long by particle standards, roughly 15 minutes rather than something spectacularly brief. It also means that heavier decay products such as muons or pions are not energetically allowed in ordinary neutron decay. The channel that works is the one involving a proton, an electron, and an antineutrino, and that narrow energy budget shapes everything from the lifetime to the spectrum of the outgoing particles. That slow pace is worth sitting with for a moment, because it can make the weak interaction feel almost misnamed. On human scales, 15 minutes does not sound especially quick. On the scale of unstable subatomic particles, it is remarkably leisurely. NIST says directly that the unusually long lifetime of the neutron follows from the very small recoil parameter and the small energy available for decay. The Department of Energy likewise describes free neutrons outside nuclei as unstable particles with a lifetime of about 15 minutes. So the neutron does not explode into a proton the instant it finds itself alone. It lingers, it persists, it waits through an interval that, for particle physics, is almost suspiciously patient. This is one reason free neutrons are so useful in experiments. They survive long enough to be trapped, guided, counted, and studied before they decay, even though they are unquestionably unstable in the end. Once you know that, another apparent contradiction becomes easier to understand. If free neutrons decay, why are there so many neutrons in the matter around us? Why does every ordinary nucleus not slowly shed its neutrons until only protons remain? The answer is that a neutron inside a nucleus is not the same energetic situation as a neutron drifting alone. NIST explains that the neutron-proton mass difference is comparable to nuclear binding energies, and therefore the energy available for decay depends significantly on the nuclear environment. As the review puts it, a bound neutron can have a wide range of lifetimes, including being stable. That is the key point. In some nuclei, converting a neutron into a proton would lower the total energy and beta decay can happen. In others, it would not, and the neutron remains bound and effectively stable. The neutron's fate is therefore not determined by some private timer hidden inside it. It depends on whether the total system can reduce its energy through the transformation. That environmental dependence is the reason beta decay inside nuclei changes one element into another. The Department of Energy explains that beta minus decay in a nucleus involves the weak force causing a neutron to change into a proton, producing an electron and an antineutrino, and increasing the atom's atomic number by 1. So a nucleus with the wrong neutron to proton balance can move toward greater stability by letting one neutron convert. In effect, the nucleus quietly edits its own composition. The number of total nucleons stays nearly the same, but the chemical identity changes because the proton count has increased. This is why beta decay is so important in nuclear physics, radioactive dating, and astrophysics. It is not just a side effect of instability. It is one of the main routes by which nuclei rearrange themselves to become more stable configurations. There is also a broader historical significance to the decay products themselves. The antineutrino is easy to treat as an afterthought because it is so difficult to detect, but its existence was one of the great conceptual rescues in early particle physics. NIST recounts that Pauli proposed the neutrino to resolve the problem of the continuous energy distribution of electrons emitted in beta decay. If a neutron had decayed into only a proton and an electron, the electron's energy would have been fixed by simple conservation laws. But experiments showed a spread of electron energies. The missing energy and momentum were being carried away by another particle. That realization did not just explain neutron decay. It opened the door to the neutrino as a whole new family of particles. So when a free neutron falls apart, it does not merely turn into a proton plus one visible electron. It quietly reenacts one of the classic arguments that help force particle physics to enlarge its cast of characters. Free neutron decay also matters far beyond the laboratory because it helped shape the early universe. NIST states that neutron decay influences Big Bang nucleosynthesis through the neutron to proton ratio, and that the neutron lifetime helps determine how many neutrons remain available for light element formation, especially helium-4, as the universe cools. NIST's current project page says the neutron lifetime still contributes the largest uncertainty in theoretical calculations of primordial helium abundance from Big Bang nucleosynthesis. So the free neutron's willingness to decay is not merely a technical curiosity. In the first minutes of cosmic history, as matter cooled and the first nuclei formed, the neutron lifetime influenced how many neutrons survived long enough to be locked into helium and other light nuclei. A slightly different neutron lifetime would have changed the balance of early element formation. The quiet decay of the free neutron therefore reaches all the way back to the chemistry of the young universe. It also reaches into present-day precision tests of the Standard Model. NIST says that neutron decay is well described in the Standard Model, and that accurate lifetime measurements are essential for testing the model, and for an independent test of the unitarity of the quark mixing matrix. ORNL makes the same point in public-facing language, noting that the neutron lifetime is an important parameter, because it enters calculations involving quark decay rates, and that any mismatch could hint at new physics. The Department of Energy likewise says that comparing experimental measurements of neutron decay with theoretical predictions can reveal so far undiscovered interactions. So the free neutron's decay is not merely something physicists timed once and filed away. It remains one of the cleanest weak interaction laboratories available, precisely because the neutron is simple enough to study and complicated enough to matter. That is why the neutron lifetime puzzle has attracted so much attention. Two main approaches are used to measure the lifetime of a free neutron. NIST explains the beam method as counting decay protons inside a known region while continuously monitoring the neutron flux, and ORNL describes the same basic idea by saying that one method counts protons appearing in a beam as neutrons decay. The other class of experiments uses ultra-cold neutrons stored in traps or bottles and measures how many survive after a certain time. NIST's review describes these as confined ultra-cold neutron measurements, and ORNL summarizes them as trapping neutrons in a magnetic bottle and counting their disappearance. In principle, both methods should converge on the same lifetime. In practice, they have not done so cleanly. As of early this year, the disagreement was still a live problem rather than a historical footnote. A January 2026 CERN Courier report on the PSI workshop says free neutrons live about 880 seconds, and that the most precise averages from beam experiments and magnetic bottle traps are about 888.1 seconds and 877.8 seconds, a discrepancy at roughly the 5 sigma level. The same report says new results from Los Alamos, NIST, JPARC, and PS Omni are expected to clarify the situation in the coming years. PSI workshop materials from September 2025 describe the discrepancy as about 10 seconds and about 4.5 sigma, and note that new beam and bottle experiments are being designed specifically to probe systematics at the few tenths of a second level. So the present state of the field is not that nobody knows the neutron lifetime at all. It is that two very careful ways of measuring it still disagree more than they should. There is a temptation, whenever a precision discrepancy like that survives long enough, to imagine that the neutron is secretly doing something exotic behind everyone's back. Physicists have certainly explored such possibilities. ORNL describes one example, a search for oscillations into hypothetical mirror neutrons, motivated in part by the lifetime puzzle. But the January 2026 CERN Courier report also says that other studies have largely excluded the possibility that the beam bottle discrepancy is explained by hypothetical exotic decay channels or other non-standard processes. Los Alamos, for its part, reported in July 2025 that its UCN2 bottle-style experiment had reached a world record precision with a measured free neutron lifetime of 877.83 seconds and uncertainty under 0.3 of a second, strengthening the bottle side of the comparison rather than making the discrepancy disappear. So for now, the cautious view is still the sensible one. The puzzle is real, the measurements are improving, and the answer may turn out to be subtle experimental systematics rather than an entirely new sector of nature. But the door has not yet been shut by final consensus. All of this gives the free neutron an oddly balanced personality. It is simple enough that its main decay mode is textbook material. It is complex enough that measuring its lifetime has occupied generations of experiments. It is unstable enough to fall apart on its own, yet stable enough to wait around for many minutes before doing so. It can be essentially permanent inside the right nucleus and temporary in isolation. It decays through the weak interaction, but understanding that decay in full precision still requires careful treatment of electro-weak effects, detector systematics, trapping losses, and the exact counting of very reluctant particles. The Department of Energy notes that recent theoretical work has uncovered relatively large corrections in neutron decay arising from the interplay of the weak and electromagnetic forces, which is another reminder that even this apparently simple process contains layers of subtlety once one asks for exact answers rather than broad sketches. So when a neutron falls apart, what we're really seeing is a compact summary of modern physics in action. A quark changes flavour through the weak force. A proton appears where a neutron used to be. An electron and an antineutrino share the available energy. The outcome depends on tiny mass differences, on the structure of the standard model, and on whether the neutron was free or bound inside a nucleus. The process matters for cosmology, for reactor physics, for tests of quark mixing, and for the stability patterns of nuclei across the periodic table. And because no one can simply open a neutron and watch the event from the inside, everything we know about this transformation has been built from clever indirect measurements, from beams and traps and detectors, and long, patient arguments with statistics. Which is a good place to pause, because once the neutron's decay has shown how much information can be pulled from particles that no one can hold still or inspect directly, the next question becomes almost unavoidable. How do physicists peer inside something this small at all, and what kind of evidence lets them describe a hidden interior they can never literally see? At some point in every discussion of particles, someone quite reasonably wants to know when the seeing part begins. We have talked about quarks, gluons, seas of virtual pairs, spin structure, charge distribution, and mass emerging from confined energy. All of that can sound suspiciously like an elaborate description of a room no one has ever entered. And in a literal sense, that suspicion is justified. No one has ever opened a neutron and looked inside the way a watchmaker opens a case or a mechanic lifts a hood. Physicists do not see the neutron's interior directly. They infer it. They reconstruct it from collisions, recoil particles, scattering angles, energy transfer, decay products, polarization patterns, and a formidable amount of theory. Brookhaven says the future electron-ion collider will take three-dimensional precision snapshots of the internal structure of protons and atomic nuclei, and Jefferson Lab says one of its major goals is to provide a detailed three-dimensional picture of the nucleon in terms of quark and gluon constituents. The key word in both cases is picture, not photograph in the everyday sense. What physicists build is a model-based image, extracted from how particles respond when probed under controlled conditions. That is why the title here includes brave guesses. The guesses are brave because the target is extremely small, quantum mechanical, and never available in the friendly cooperative way laboratory objects usually are. But they are still educated guesses, constrained by data, sharpened by mathematics, and often punished harshly when they fail. The Department of Energy says theoretical calculations help scientists understand how mass is distributed among hadrons and provide direction for upcoming experiments, while another Department of Energy article describes lattice quantum chromodynamics as a method that simulates hadron structure on supercomputers. So the guessing part in modern particle physics is not a wild leap into the dark. It is the disciplined part of science where one builds a quantitative description and then asks the universe to prove it wrong. The neutron has survived that treatment impressively well, though not always in the simple form people first expected. The main experimental trick for peering inside the neutron is scattering. This idea goes back to one of the oldest habits in physics. If you want to know what something's like on the inside, you throw something at it and study how the projectile comes back. Rutherford did this with atoms and discovered nuclei. In the late 1960s and early 1970s, deep inelastic scattering of high-energy electrons from protons and bound neutrons provided the first convincing evidence that nucleons contain point-like constituents, what we now call quarks. The Nobel lecture on deep inelastic scattering says the ASLEC experiments used high-energy electrons on hydrogen and later deuterium targets to probe the nucleon, and it describes this work as essential to revealing internal quark structure. Jefferson Lab's public description of the marathon program says deep inelastic scattering means bombarding nuclei with electrons so violently that the nucleons are effectively broken open, and their internal quark distributions can be inferred from the scattered electrons and produced particles. In short, the neutron gave up its first secrets not because anyone saw a quark sitting inside it, but because collision data behaved as though electrons were striking smaller charged constituents within the nucleon. There is, however, a practical annoyance when the target of interest is specifically the neutron. Free neutron targets do not really exist in the friendly, stable way proton targets do. A proton can sit in a bottle of hydrogen and behave itself. A free neutron decays, and even before that it is harder to contain and use. Jefferson Lab material on neutron structure says explicitly that free neutron targets are unavailable, and that neutron measurements therefore rely on nuclear targets, typically deuterium. Other Jefferson Lab material on neutron studies makes the same point by explaining that most experiments get at neutron structure through nuclei rather than isolated neutrons. This is why neutron physics often feels a little more indirect than proton physics. To study a neutron, physicists usually study a simple nucleus containing one and then work carefully to separate neutron information from the nuclear environment surrounding it. The simplest such nucleus is deuterium, or heavy hydrogen, which contains one proton and one neutron. Jefferson Lab describes the deuteron as the simplest bound system of neutrons and protons. That simplicity makes it a natural stepping stone toward neutron structure, but not a perfect one. If you scatter an electron from deuterium, you are probing a neutron inside a bound system, which means nuclear binding and motion can blur the answer. Jefferson Lab's spectator tagging program exists precisely because of this problem. Its description says the method uses deep inelastic scattering on the deuteron, with detection of the spectator proton, allowing researchers to identify events where the electron interacted mainly with the neutron while the proton stayed out of the way. Jefferson Lab proposals for tagged deep inelastic scattering say the point is to isolate scattering from a nearly on-shell neutron and reduce nuclear model uncertainties. That is a lovely example of particle physics ingenuity. If you cannot obtain a free neutron target, you look for an electron hitting the neutron while the proton merely watches from the sidelines. Then you use the spectator proton as evidence that the neutron was the real target of the blow. There are other nuclear stand-ins as well, and each comes with its own advantages. Helium-3 is a particularly useful one when spin enters the story. Jefferson Lab explains that helium-3 contains 2 protons and 1 neutron, and when the nucleus is polarized, the proton spins tend to cancel, so that the neutron carries most of the nuclear polarization. Brookhaven said the same again just this month when describing planned electron-ion collider work, noting that polarized helium-3 nuclei give scientists access to neutron spin because the net polarization is held mostly by the single neutron. That makes helium-3 a remarkably practical effective neutron target for spin measurements. It is not the same as a lone neutron, and physicists still have to correct for nuclear effects, but it is often the cleanest path available. In this field, one learns to appreciate any target that is merely difficult instead of impossible. Mirror nuclei provide another useful route. Jefferson Lab's marathon work used helium-3 and tritium together because they are mirror nuclei, with helium-3 containing 2 protons and 1 neutron, and tritium containing 1 proton and 2 neutrons. Jefferson Lab says the value of the comparison is that theoretical uncertainties are expected to cancel to a large extent in ratios built from these mirror systems. That cancellation helps physicists extract the neutron to proton structure function ratio more cleanly than they could from a single nucleus alone. This is a good example of how experimental nuclear physics often proceeds. One does not wait for perfect conditions because perfect conditions do not arrive. One designs pairs of measurements whose imperfections partly cancel, and then one interprets what remains. The neutron, being inconveniently bound and inconveniently unstable, has forced physicists to become rather good at this style of indirect honesty. Scattering itself comes in several flavours, and each reveals a different layer of the neutron's interior. Elastic scattering leaves the nucleon intact and is used to measure form factors, which encode information about charge and magnetization distributions. Jefferson Lab says electromagnetic form factors are fundamental for understanding the distribution of charge and magnetization within nucleons, and its neutron charge program says precise measurements of the neutron electric form factor have put neutron charge structure on nearly equal footing with the other nucleon form factors. Deep inelastic scattering, by contrast, transfers enough energy that the nucleon is broken open and the experiment becomes sensitive to Parton distributions, meaning how quarks and gluons share momentum inside the neutron. Jefferson Lab's generalized Parton distribution program says these distributions unify ideas from elastic form factors and deep inelastic Parton distributions, allowing a more complete three-dimensional description. So the choice of experiment depends on the question. If you want to know how charge is arranged, you use one class of tools. If you want to know how momentum is shared among quarks and gluons, you use another. If you want both at once, physics makes you work harder and invent a new framework. This is where the brave guesses become especially important, because raw detector signals are not self-interpreting. An experiment does not simply flash a message saying 2 down quarks and 1 up quark, C contribution present, spin decomposition unclear. What it gives are cross-sections, asymmetries, recoil tracks, energy deposits, timing signals, and angular distributions. To turn those into statements about the neutron's interior, physicists need theory. Jefferson Lab says generalized Parton distributions are a framework for extracting a detailed three-dimensional picture of quark and gluon structure, while the Department of Energy says lattice quantum chromodynamics and related calculations provide direction for upcoming experiments and help interpret what is being measured. This is the part of the story that can make outsiders uneasy. It sounds as though theory is being used to tell the data what to say. In good science, though, the relationship is more balanced than that. The theory proposes a pattern. The data test whether nature follows it. If not, the theory is revised, not the other way around. The guesses are brave because they go beyond immediate observation. They are respectable because they can be falsified. One should also say something kind about detectors here, because they are the unsung translators in this business. Modern scattering experiments do not work with a single counter and a hopeful expression. They rely on large systems that track charged particles, measure energies, identify particle types, and reconstruct collision events from many fragments. Brookhaven describes the time projection chamber at STAR as acting like a three-dimensional camera for subatomic particles, and Brookhaven says the electron-ion collider will rely on detectors that can produce three-dimensional images of quark and gluon structure. Jefferson Labs' public descriptions of CLAS and related instruments emphasize that scattered electrons and recoil particles are captured with state-of-the-art detector systems. This is how one gets from invisible events to quantitative structure. You do not photograph a quark. You record the debris and build back toward the cause. The process is less like peering through a microscope and more like reconstructing a complicated accident from tire marks, bent metal, and witness accounts, except that the witnesses are silicon trackers and calorimeters, and the accident happens millions of times under carefully repeated conditions. The next major step in this story is the electron-ion collider. Brookhaven says scientists are building this machine to peer inside atomic nuclei and inside the individual protons and neutrons that make up the nucleus. Its science pages say the collider will use high-energy polarized electrons and ion beams to take three-dimensional precision snapshots of internal structure and cast fresh light on the forces that bind protons and neutrons together. Brookhaven also says the facility will be hosted at Brookhaven National Laboratory, and its electron-ion collider pages describe it as a unique high-energy, high-luminosity polarized collider. The emphasis on polarized beams matters because spin-dependent measurements are crucial for disentangling how quarks and gluons contribute to nucleon structure. The emphasis on ions matters because nuclei are not just bags of protons and neutrons, but places where quark and gluon distributions can be modified by the nuclear environment. For neutron science in particular, the electron-ion collider promises cleaner access through light ion beams, polarized helium-3, and the ability to study both individual nucleons and nuclei in the same machine. It is, in effect, the next great microscope for the quiet particle we have been following all along. There is one final point worth making before we leave the experimental side of the neutron. Physicists do not really peer inside in the everyday sense at all. What they do is build overlapping ways of being wrong, then see which ways survive. Deep inelastic scattering revealed quark-like constituents. Elastic scattering revealed form factors. Polarization measurements exposed spin structure. Spectator tagging reduced nuclear ambiguity in deuterium. Mirror nuclei comparisons squeezed uncertainties from neutron to proton ratios. Lattice quantum chromodynamics tested whether the underlying theory can reproduce the observed hadron world from first principles. The electron-ion collider is being built because the present picture is already strong enough to ask better questions, not because the old picture was meaningless. Brookhaven says the collider will zoom in beyond the simplistic image of three valence quarks, while Jefferson Lab says its goal is to understand how complex quark and gluon structure leads to familiar properties such as mass, spin, and magnetic moment. That is the spirit of the whole enterprise. The brave guesses become less brave over time because each new beam and detector narrows the room in which error can hide. So when we say physicists have looked inside the neutron, what we really mean is something both humbler and more impressive. They have built machines capable of hurling electrons at matter with extraordinary precision. They have learned to use deuterium, helium-3, and tritium as imperfect stand-ins for neutrons that refuse to be bottled like well-behaved targets. They have watched what comes back from collisions, measured asymmetries and recoil particles, compared results across many experiments, and used theory to connect those observations to quarks, gluons, charge distributions, spin structure, and mass generation. They have not opened the neutron. They have cornered it intellectually. And that is close enough to seeing for science to move forward, because once the interior can be inferred with enough consistency from enough different angles, the neutron stops being an opaque object and becomes a place with a map, even if the map is still being revised in the margins. Which leaves us with the last question in this journey. After all the collisions, all the models, and all the careful reconstructions, is a neutron ever really still at all? Or is its deepest identity nothing more and nothing less than a lasting pattern of motion held together for a while by the strongest rules in nature? By the time we reach this question, the neutron has stopped looking like a simple object and started looking like a negotiation that nature somehow keeps winning. We began with the quiet particle in the heart of matter, moved inward through valence quarks, gluons, confinement, the restless sea, spin, charge, mass, decay, and the experimental tricks physicists use to reconstruct a hidden interior. At every step, the same lesson kept returning in different clothes. The neutron is not empty, not inert, not built like a tiny mechanical toy with fixed pieces resting politely side by side. It is active inside. It is structured by motion. It is held together by interaction. So when we finally ask whether a neutron is ever truly still, the honest answer depends very much on what kind of stillness we mean. In ordinary life, stillness is not a very difficult idea. A book on a table is still. A parked bicycle is still. A sleeping cat is still in the useful everyday sense, even if the ears occasionally twitch, and there is the distant possibility of sudden moral outrage if one opens a packet of food in the next room. We call something still when its overall position is not changing in any obvious way, and when its internal activity is small enough to ignore. That definition works beautifully for the world of furniture, household objects, and most social situations. It works much less well for quantum particles. A neutron can be at rest in the sense that its total momentum is zero. You can prepare neutrons moving slowly enough to trap them. You can talk about the rest frame of a neutron, meaning the frame in which the neutron as a whole is not travelling through space. But once you've done that, the deeper question begins: is it still on the inside? Everything we have learned says no, not in the classical sense. Even when a neutron is at rest as a whole, its constituents are not sitting motionless in some tiny frozen arrangement. The valence quarks carry momentum. The gluon field is active. Quark-antiquark pairs flicker in and out as part of the sea. Angular momentum is shared among quark spin, gluon contributions, and orbital motion. The mass of the neutron itself comes largely from this internal activity, from confinement energy and the dynamics of the strong interaction, not from a simple sum of bare constituent masses. So the neutron can be still only in the very limited sense that the whole object is not translating through space. Internally, stillness is the wrong word. There is a useful distinction here between rest and inactivity. In classical thinking, those ideas often travel together. A wheel at rest is not turning. A ball at rest is not rolling. A pendulum hanging straight down is not swinging. But quantum systems are not obliged to preserve that partnership. A particle can be in a stable state, without its internal degrees of freedom becoming motionless in the ordinary sense. The neutron is one of the clearest examples. It has definite mass, a definite spin, a definite magnetic moment, and in many contexts a long-lived identity. Those facts make it stable enough to treat as an object. But the way those properties arise is inseparable from internal motion and field activity. The neutron is stable because its structure persists, not because its interior becomes quiet. That can feel counterintuitive because we are used to treating motion as something that disturbs a system from its natural resting state. In the neutron, motion is part of the resting state. Confinement does not produce a neat static arrangement. It produces a bound quantum state in which the quarks are localized within a very small region and therefore necessarily carry significant momentum. Even without writing down the formal mathematics, one can understand the basic point. If you confine quantum constituents tightly in space, you do not get perfect stillness in momentum. You get the opposite. Tight localization and low internal motion do not go together. So the neutron's interior is busy partly because it is small. It is not merely that the strong force is intense, it is that the strong force is confining the system so strongly within such a tiny region that quantum motion is unavoidable. This is one reason the neutron feels so different from older images of matter made from little hard beads. If the neutron were truly a miniature solid pellet, then asking whether it is still would make as much sense as asking whether a grain of sand is moving when it rests on a windowsill. But the neutron is not a pellet. It is a bound state of quarks and gluons. Its identity lies in an arrangement of fields and allowed quantum numbers that persist over time. The persistent thing is the pattern, not the absence of motion. A good comparison, though not a perfect one, is a musical note held by a violin. The note can be steady. It can have a definite pitch and recognizable identity. But it exists only because something is vibrating. Remove the motion, and the note does not become a quieter note. It disappears. The neutron is not a sound, and does not rely on strings and bows, but the logic is similar. Its apparent solidity comes from ongoing internal dynamics, not from their absence. This is also why the neutron's mass and stillness are connected in such an interesting way. In many everyday cases, mass feels like a sign of substance at rest, the amount of stuff in an object. In the neutron, most of the mass is energy from quark motion and gluon fields, so the very thing that makes the neutron seem substantial is tied directly to its internal activity. If the quarks and gluons inside a neutron somehow became perfectly still, in the classical sense, you would not obtain a calmer neutron. You would lose the conditions that give the neutron most of its mass and structure in the first place. The heaviness of ordinary matter depends on microscopic restlessness. That is one of the quietest and most surprising truths in modern physics. The stable world around us owes its weight to things that never really settle down. There is another layer to the question though, because stillness can also mean changelessness. Does a neutron remain the same over time? Here the answer is again qualified. Inside a stable nucleus, a neutron can remain part of that nucleus for an immense duration. As a free particle, it does not last forever. It decays by the weak interaction into a proton, an electron, and an antineutrino. So even the neutron's identity is not absolutely fixed in every context. It is durable, but not eternal. In a nucleus, the surrounding energy balance can make the neutron effectively stable. In isolation, the particle has another allowed path and eventually takes it. That means the neutron is not still even in the deeper sense of being immune to transformation. It is better described as metastable in one setting and stable in others, always depending on the conditions that surround it. This dependence on context is very important, because it saves us from imagining that every neutron carries a little hidden countdown clock, independent of the world around it. Particle physics is less theatrical than that. What matters is which states are allowed by the underlying interactions and whether a transition lowers the energy of the total system. A free neutron is slightly heavier than a proton, so the weak decay can proceed. A bound neutron may or may not be able to make the same transition depending on the nucleus it inhabits. The lesson is not that the neutron cannot decide who it is. The lesson is that identity in particle physics is relational. What a particle can do depends on the system it belongs to. Stillness, then, is not merely about internal motion. It is also about whether the particle sits in a context that lets it remain what it is. The spin of the neutron adds yet another twist. Spin is intrinsic angular momentum, not literal tiny spinning in the classical sense, but it is still a property that refuses the image of perfect internal stillness. A particle with spin has a directional character built into its quantum description. The neutron's magnetic moment reflects the motion and arrangement of charged quarks inside it. Its spin structure is shared among several internal components, rather than being trivially assigned to the valence quarks alone. So even the most basic labels attached to the neutron point away from stillness and toward organized internal motion. To say that a neutron has spin is already to say that it possesses a kind of quantum liveliness not captured by the image of a little inert ball. Then there is the sea. It is worth returning to that, because the sea may be the strongest reason not to call the neutron still. The valence quarks define the neutron's main identity, but the sea of gluons and transient quark-antiquark pairs is always present as part of the bound state. This does not mean individual particles are entering and leaving in the everyday sense like commuters on a platform. It means the quantum fields inside the neutron continually support fluctuations and exchanges that contribute to momentum, spin, mass and structure. A neutron is therefore not a particle with a quiet centre and a noisy edge. It is noisy all the way through, though noisy is perhaps unfair because the activity is highly constrained and not at all random in the sloppy everyday sense. It is better to say that the neutron is dynamically populated. Its identity includes a persistent cloud of interactions rather than a silent emptiness surrounding three named constituents. There is a temptation at this point to ask whether anything in quantum physics is ever truly still. That is a larger question than we need tonight, but the neutron certainly suggests that stillness is rarely fundamental at small scales. What we often call stillness is really stability. It is the persistence of a pattern through time. A stable atom is not a static little solar system. A stable crystal is not a perfectly frozen arrangement with no microscopic motion at all. A stable neutron is not a silent bead. Stability means the object keeps its recognizable identity under the rules available to it. Internal motion and field activity are not exceptions to that stability. They are often the reason it exists. This way of thinking can sound unsettling at first, because it asks us to give up a very old comfort. We like the idea that beneath complex visible things there must be simple quiet pieces. It feels explanatory. Tables are made of wood. Wood is made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are made of subatomic particles. Surely at some point we arrive at the truly still little units from which the restless world is built. The neutron does not grant that wish. It tells us that the deeper level may be less like a collection of still pieces and more like a persistent choreography. The object remains, but what remains is a form of motion held together by rules. That is not mere metaphor, it is a practical scientific statement. When physicists calculate neutron properties, they do not do so by assigning 3 tiny marbles a set of fixed locations and then taking an early lunch. They work with quantum states, field interactions, pattern distributions, form factors, lattice calculations, and scattering amplitudes. Everything about the formalism reflects the fact that the neutron is a system of activity. The experiments do the same. Elastic scattering probes distributions of charge and magnetization. Deep inelastic scattering probes how momentum is shared among constituents. Polarization measurements probe spin-dependent structure. All of those methods assume that the neutron's interior is active enough to leave measurable signatures in collision data. No one would build such a large experimental enterprise if the correct model was simply that the neutron is a neutral pellet with commendably few hobbies. Even the most still neutron humans can prepare in the laboratory is not really still in the deepest sense. Ultra-cold neutrons can be slowed to very low speeds. They can be stored in magnetic traps or material bottles. Their motion through the apparatus can be reduced enough that they seem, by experimental standards, almost at rest. Yet all that slowing applies to the neutron as a whole. It says nothing about the quark and gluon dynamics inside. One can trap the particle, not freeze its internal quantum structure. The outer stillness is useful for measurement. The inner restlessness remains. That contrast is almost poetic, though I know we have promised not to wander too far into abstraction. It is better to say simply that the experimenter can calm the neutron's travel without silencing the physics that makes it a neutron. There is also a larger philosophical reward in answering the question this way. If a neutron is not truly still, then matter itself is not built from stillness. It is built from durable activity. The visible world, which feels solid and settled and dependable enough for cups, books, roads, houses, and human routines, rests on systems that are never fully at rest in the classical sense. Quarks move, gluons bind, fields fluctuate, energy becomes mass, decay remains possible, and yet the world holds together. That should not make us trust it less. If anything, it makes the achievement more impressive. Stability is not the absence of motion. It is motion arranged so well that structure persists. So in the end, is a neutron ever truly still? If you mean, can the neutron as a whole be at rest relative to an observer, then yes. That much is perfectly sensible. If you mean, does its interior ever become a quiet classical arrangement with no motion, no exchange, no fluctuation, and no dynamical structure, then no. Absolutely not. The neutron at rest is still busy. It keeps its mass through internal energy. It keeps its spin through shared angular momentum. It keeps its magnetic character through moving charges and quantum structure. It keeps its identity only because the strong interaction never really takes the evening off. That turns out to be a satisfying place to leave the question, because it brings the neutron back into contact with the larger lesson of modern physics. The deeper we look, the less nature resembles a warehouse of tiny silent objects, and the more it resembles a hierarchy of stable patterns, each built from interactions at the level below. The neutron is one of those patterns. It is real. It is measurable. It can be trapped, scattered from, counted, and in many nuclei preserved for extraordinary spans of time, but is not still in the old mechanical sense. It is a sustained structure, a small and very disciplined commotion held together by the strongest rules we know. And perhaps that is the most honest answer the neutron offers. Stillness, at the deepest level we can currently reach, may not be what matter is made from at all. What persists is not silence, but order. Not emptiness, but balance. Not a frozen core, but a lasting arrangement of motion. The neutron seems quiet only from a distance. Up close, it is one more reminder that the universe does not build stable things by making them lifeless. It builds them by letting them move in exactly the ways it allows, and by refusing every other possibility.